It would be strange to be gazing at a tiny star 120 light-years away in the constellation Leo and find that one of its planets might be living. There is a 99.7% chance of life, which was proven by the James Webb Space Telescope. It has nothing to do with cities or satellites. No, this is not science fiction. This is K218b, an ocean world covered in hydrogen that whispers gases through its atmosphere that we've only ever seen coming from living things on Earth. It's possible that this signal will stay strong and change everything we thought we knew about life in the universe. Where is K218b, locating this ocean world in the cosmos? K218b is 120 light-years away from Earth. That may sound like a long way, but in the grand scheme of things, it's actually pretty close. The star is in the constellation Leo, which is only 720 trillion miles away, and is usually associated with astronomy rather than astrobiology. But right there, around a faint red dwarf star called K218, is a world that might have the best conditions for life we have ever seen outside of Earth. To understand where K218b is, you first need to understand the kind of star it orbits. K218 is a red dwarf, much cooler and smaller than our Sun. These stars make up about 75% of the stars in our galaxy. They're abundant, they burn slowly, and they live for trillions of years. That's good news for any planet orbiting them, because it means stable energy for a very long time. However, red dwarfs often flare, shooting out bursts of radiation, which can complicate things for life. But K218 appears to be unusually quiet for a red dwarf, giving its planets a better chance. K218b was originally discovered by the Kepler Space Telescope's K2 mission back in 2015. That's where it gets its name, K2 from the mission, and J18b, because it was the second planet discovered in that particular system. The B denotes a planet, and 18 identifies the host star in Kepler's catalogue. K218b circles its star once every 33 days. That might sound fast compared to Earth's 365-day orbit, but remember, its host star is much smaller and cooler than the Sun. That means the habitable zone, the Goldilocks zone where liquid water can exist, is much closer in. K218b sits comfortably in that zone, bathing in just enough stellar energy to potentially keep an ocean of water from freezing or boiling away. In terms of size, K218b is a super-Earth or a mini-Neptune, roughly 2.6 times the radius of Earth and about 8.6 times its mass. So if Earth is a marble, K218b is a small melon. It's bigger, heavier, and has stronger gravity, but not so much that it crosses into full gas giant territory. This puts it in a fascinating middle category of exoplanets that don't exist in our solar system. Of particular interest is the fact that K218b doesn't move around by itself. At least one more planet, K218c, is in the K218 system. It is smaller and closer to the star, but it is not in the habitable zone. That means K218b is the best place to look for alien life. In skywatching terms, if you want to find K218b in the night sky, you'd need to look toward the Leo constellation, which rises in the east during spring in the northern hemisphere. Of course, you can't see the planet with your eyes, or even with most telescopes, because the star it orbits is so faint. K218 is about magnitude 13, meaning it's roughly 16,000 times dimmer than the faintest star visible to the naked eye. So while this exoplanet may be making headlines, it's completely invisible to us without the help of high-powered space observatories. The planet is so far away that even the James Webb Space Telescope can't take a picture of it. Instead, we know it exists because of a method called transit spectroscopy. When the planet passes in front of its star from our point of view, it dims the starlight just a little. That dimming tells us the planet is there, but more importantly, the light that filters through the planet's atmosphere during the transit can be analyzed. Like sunlight through a stained glass window, it carries the fingerprints of whatever gases are in the air. That's how we know K218b has water vapor, and maybe even more. What type of planet is it? The Hycean world hypothesis. K218b doesn't seem to belong to any of the types of planets we know about from our solar system. There are no rocks on it like there are on Earth, and it's not a gas giant like Neptune or Jupiter either. Instead, experts think it might be a Hycean world, which is a completely different type of planet and could help us learn a lot more about where life might live. Let's break that down. Hycean is a portmanteau of hydrogen and ocean. It refers to a planet that has two key features: a hydrogen-rich atmosphere and a global liquid water ocean underneath. This combination could create habitable conditions, even if the planet looks nothing like Earth. The idea of Hycean planets was first formally proposed in 2021 by researchers like Niku Madhusudan at the University of Cambridge. Their models suggested that planets larger than Earth but smaller than Neptune could still have oceans, and that their hydrogen-dominated skies could make the detection of life signature gases even easier than on Earth-like worlds. K218b is a very strong possibility because of this. Its size and mass are just right for Hycean, big enough to keep a thick atmosphere, but not so big that it turns into a gas giant. Infrared data from the James Webb Space Telescope shows that its atmosphere has water vapor, methane, carbon dioxide, and maybe even dimethyl sulfide, DMS, a molecule that is mostly made by living things in the ocean on Earth. If K218b really is a Hycean planet, it could mean that oceans and life can exist under completely different atmospheric conditions than we're used to. We're talking about alien oceans covered by skies full of hydrogen gas. It's like an Earth flipped inside out, a planet wrapped in chemistry that we once assumed was hostile to life, but may in fact be ideal for detecting it. Why does hydrogen matter so much? For one, hydrogen is a light molecule, so it creates large-scale heights in the atmosphere. That means the planet's atmospheric layers are puffier and more spread out, making them easier to analyze when light passes through them during a transit. Even tiny amounts of gases like methane or DMS can stand out more clearly than they would in a nitrogen-oxygen atmosphere like Earth's. To put it simply, a hydrogen environment acts like a booster for biological signals. But this also brings up a more important question. Can life live in an environment mostly made up of hydrogen? We're used to oxygen and nitrogen on Earth, but life can adapt to a lot of different conditions. Right now, there are microbes on Earth that live in places with a lot of hydrogen, like deep-sea volcanic vents. Hydrogen and methane are broken down by these living things to make energy in conditions that would kill most surface life. So the idea isn't that life on K218b would be like us. It wouldn't be breathing oxygen or basking in sunshine. Instead, it might look more like Earth's extremophiles, primitive organisms that thrive in chemical soups, feeding off hydrogen, CO2, and other gases in total darkness. Hycean worlds also come in two main flavors: hot Hycean planets that orbit close to their stars, and cold or dark side Hyceans that may be tidally locked, with one side permanently in darkness. K218b may fall somewhere in between. It orbits in the habitable zone of its star, meaning it gets just the right amount of heat to keep water in liquid form. But if it's tidally locked, and we don't know for sure yet, it might have a permanent day side and night side, leading to wild temperature differences and potentially exotic weather systems. Hycean planets may be far more common than Earth-like ones. Astronomers have found that planets in the 2 to 3 Earth radius range, the same size as K218be, show up frequently in exoplanet surveys. That means we may have been looking in the wrong place all along. Earth-like planets are rare, but Hycean planets? They might be everywhere. If there are a lot of Hycean planets, and they can have oceans and life, then the universe is much more living than we thought. We no longer need to find a perfect Earth twin. We just need to find more planets like K218b. Planets that are wrapped in hydrogen and have oceans that float beneath foreign skies. On these planets, biosignatures can be seen rising through the clouds. The role of the James Webb Space Telescope in the discovery. James Webb Space Telescope, JWST, made all of the distinction. K218b had already been in the news before JWST. Before JWST looked at it, this planet wasn't a new find. We already knew it circled a red dwarf star in the habitable zone. But we didn't know how strange it could be until JWST ripped its atmosphere apart like a crime scene in space. A world we thought was interesting all of a sudden became one of the best places to look for alien life. JWST was launched in December 2021 and became fully operational by mid-2022. Its suite of infrared instruments allows it to do what no previous telescope could: see through clouds of gas and dust, pick apart light at incredible precision, and detect the faintest chemical traces in exoplanet atmospheres. Unlike the Hubble Space Telescope, which can dabble in visible and near-infrared, JWST is optimized for deep infrared, making it especially sensitive to molecules like water vapor, methane, carbon dioxide, and even dimethyl sulfide, DMS. When K218b passes in front of its host star, something called a transit, a small portion of the star's light filters through the planet's atmosphere before reaching our telescopes. That light isn't just dimmed, it's changed. Molecules in the atmosphere absorb specific wavelengths of light, creating a fingerprint-like pattern in the spectrum. JWST's instruments like NIRSpec, near-infrared spectrograph, and NIRIS, near-infrared imager and slitless spectrograph, can detect these patterns with unmatched sensitivity. With Hubble, we got a rough sense of water vapor in the atmosphere back in 2019. That alone made K218b intriguing, but JWST took that 1,000 steps further. Its readings didn't just confirm water vapor, they uncovered the possible presence of methane and carbon dioxide, which suggested a much richer chemical environment. But the biggest bombshell was the detection of dimethyl sulfide, or DMS, a gas that, on Earth, is only produced by biological processes, mainly by phytoplankton in the ocean. That finding, if confirmed, would be completely unprecedented. No telescope had ever detected anything close to a biosignature gas on a planet in the habitable zone. The closest we'd gotten were hints of oxygen or methane on other worlds, but always with caveats and never with this level of precision. JWST took us from maybe to possibly yes, and that shook the foundations of planetary science. The detection didn't happen by accident. JWST targeted K218b intentionally as part of a program to test its transmission spectroscopy capabilities on potentially habitable worlds. K218b was a top target because it's large enough to have an extended atmosphere, which makes signals easier to read. And it orbits a dim red dwarf, so the contrast between the planet and its star isn't overwhelming. It was the perfect proving ground. What JWST captured wasn't just data. It was an entirely new level of atmospheric modeling. Scientists had to run complex simulations to interpret what the spectra meant. They didn't just say, "We see methane." They said, "The combination of methane, carbon dioxide, and DMS, with no sign of ammonia, strongly suggests non-abiotic processes." In other words, it's not just about what they saw, but what was missing that made the results compelling. JWST also ruled out simpler, abiotic explanations for the data. In most planetary atmospheres, you don't expect to see this combination of gases unless something is constantly replenishing them, something alive. And because the telescope's instruments are so advanced, the margin of error in these detections is lower than ever before. But JWST didn't just study K218b once and call it a day. These observations were part of a longer-term monitoring plan, with more transits scheduled for the coming years. Each new pass gives scientists a better signal-to-noise ratio, helping to confirm or refute what they've seen so far. That's crucial, because any claim of alien life, even microbial, even just a chemical trace, needs ironclad evidence. And the telescope's role doesn't stop at detecting gases. JWST can also help determine temperature, cloud coverage, pressure profiles, and even vertical layering of the planet's atmosphere. It's like building a weather report for a planet 120 light-years away, and doing it with more accuracy than we can sometimes manage on Earth. With the old tools, none of this would have been possible. It wasn't possible with the Spitzer Space Telescope. Hubble could only just pick up water mist. No matter how big they are, ground-based cameras can't avoid radiation from the atmosphere. But JWST is stuck in space, circling at the Lagrange point 2, which is a gravity sweet spot that keeps it cool, steady, and in the best place to collect light from faraway stars without Earth's air distorting it. Water vapor detected. The first sign of a breathable world. When scientists first confirmed that K218b's atmosphere had water vapor in it, it felt like the start of a new era in human history. More than just finding water on a strange world, this was the first time we had found an exoplanet that might be livable and had water in its atmosphere. It was in the Goldilocks zone of its star. In the air of a world 120 light-years away that you can't see, you could smell rain. Water vapor isn't rare in the universe. We've detected it in the clouds of Jupiter, the tails of comets, and even floating around black holes. But detecting water vapor on an exoplanet in the habitable zone, that's a whole different ballgame. That's because, for life as we know it, liquid water is essential. And the presence of water vapor in the atmosphere suggests that liquid water might exist on the surface or just below it. Back in 2019, scientists using the Hubble Space Telescope found the first hints of water vapor in K218b's atmosphere. It was a major breakthrough, but Hubble's sensitivity was limited. It could only detect broad absorption features in the near-infrared. It gave us a signal, a blurred outline, but not the full picture. It told us that something was absorbing light at the specific wavelengths where water typically leaves its fingerprint, but it wasn't sharp enough to confirm the amount or rule out other gases. Then came JWST. With its vastly superior infrared resolution, JWST not only confirmed the presence of water vapor, but also provided a much clearer spectral signature. This wasn't a maybe. It was a yes, water is here, and it's widespread. The findings were based on a detailed analysis of light that had passed through the planet's atmosphere during multiple transits across its host star. Every time the planet passed in front of the star, some of the starlight filtered through its atmosphere and was imprinted with chemical clues. JWST dissected that light with surgical precision. So why is water vapor such a big deal? First, it's a key component of a life-supporting environment. You can't have clouds, rain, or oceans without water vapor. It plays a role in climate regulation, energy balance, and surface chemistry. If K218b has a water cycle, with vapor rising, condensing into clouds, raining down, and evaporating again, it's far more Earth-like than we ever expected, and that makes it a tantalizing candidate for supporting some form of life. Second, water vapor is a clue about surface conditions. For it to exist in the atmosphere in significant quantities, the planet must have temperatures and pressures in the right range, not too hot to vaporize all water into steam, and not too cold to lock it in ice. Atmospheric models based on JWST data suggest K218b may have temperatures between 0 and 30 degrees Celsius, 32 to 86 degrees Fahrenheit, a sweet spot for keeping water in its liquid state, at least beneath the clouds. But K218b is not Earth's twin. It's a lot bigger, has a thicker atmosphere full of hydrogen, and might not have a solid surface. Instead, a lot of scientists think that underneath that humid sky is a huge ocean that covers the whole world. Imagine a warm, deep sea in another world that is covered in a blanket of hydrogen. Water vapor could be rising from the ocean and making thick clouds that move through an environment we don't fully understand yet. If there are clouds on K218b, what are they made of? The way water-based clouds reflect and spread light would be known ahead of time. Some models say that K218b's cloud layers might be thick and spread out, which could block views from the surface but make the environment interesting and full of weather. Water vapor enhances the detection of other key molecules. Many biological gases, like methane and dimethyl sulfide, have signatures that overlap or interact with water vapor. The presence of water not only supports habitability, but boosts our ability to find life-associated gases. It acts like a magnifying lens for astrobiology. The water vapor detection does not confirm oceans. It strongly suggests they could exist, but it doesn't prove a liquid surface. There could be supercritical water, a phase that's neither gas nor liquid, or a hot, pressurized layer under dense clouds. That said, the idea that there's an entire warm ocean world under those skies is one of the most exciting concepts in modern astronomy. The temperature on K218b may also be kept in check by the water mist that is there. On Earth, water vapor keeps the temperature stable by acting as a greenhouse gas. It could do the same thing for a planet like K218b, stopping its red dwarf star from being too hot or too cold. This is especially true if the planet is tidally locked, meaning that one side is always facing the star. DMS on an exoplanet, the most shocking JWST signal yet. The James Webb Space Telescope found many chemicals in the atmosphere of K218b, but dimethyl sulfide, DMS, was the one that really shocked people. If it turns out to be true, it would be the first time in human history that we've found a molecule outside of our solar system that can only be made by living things on Earth. Sometimes. No, not sometimes. Only. Dimethyl sulfide is a sulfur-based chemical. Its formula is CH3 taken twice, then S. That means it has 2 methyl groups and 1 sulfur atom dot. On our planet, more than 99% of atmospheric DMS comes from marine life, specifically phytoplankton, microscopic organisms that thrive in the sunlit layers of Earth's oceans. When these creatures break down organic sulfur compounds, they release DMS into the atmosphere, where it plays a crucial role in cloud formation and climate regulation. That last bit is wild, because DMS doesn't just exist as a byproduct of life. It influences Earth's weather. The gas helps seed clouds, which in turn reflect sunlight and regulate surface temperatures. Life literally shaping the sky. So when JWST data suggested DMS could be present on K218b, it was like hearing a whisper from a mirror world, one where the oceans might be full of microbial life doing the same thing. The detection wasn't loud. It wasn't a neon sign blinking aliens here. It was a subtle absorption feature in the infrared spectrum, buried among the fingerprints of other gases like methane and carbon dioxide. But when scientists ran the models, testing different combinations of molecules to match what JWST saw, DMS kept showing up as the best fit explanation for the observed signal. On Earth, DMS doesn't form easily without biology. It's not known to arise from volcanism, photochemistry, or even high-energy reactions in the atmosphere. That's what makes it such a tempting biosignature. While gases like methane can come from either life or geology, DMS has no known abiotic pathway that could explain its abundance in a hydrogen-rich atmosphere like K218bs. The potential DMS detection wasn't alone. It came alongside methane, CH4, and carbon dioxide, CO2. 2 other gases that, when found together with water vapor and DMS, paint a very specific chemical picture. On Earth, this trio of gases exists in dynamic disequilibrium. That means their presence requires constant replenishment, usually by biological activity. That's why some scientists are calling this the life fingerprint trio. And on K218b, that trio was found in a world that also likely has a vast global ocean and mild temperatures, adding environmental credibility to the biological explanation. But science is vigilant, which is a good thing. The DMS signal could still be noise, a mistake, or even a feature from another molecule that was read wrong. The tools made by JWST are very strong, but they're not perfect. Modeling the atmosphere is hard, and even small problems with accuracy or wrong assumptions can cause false results. If the conditions are right, sulfur dioxide, SO2, or some other unknown gas might be able to look like DMS's signal. Before this goes from being a chance to a fact, scientists need more transits, more data, and confirmations from other sources. There's also the risk of confirmation bias. After decades of searching for life, it's easy to get excited when data even suggests something biological. But the scientific community is taking this seriously, with skepticism and discipline. That's why you'll hear headlines like DMS possibly detected, not life found. The difference is crucial. Even if DMS is there, it doesn't guarantee there's life. It just makes the planet more suspiciously Earth-like than anything we've ever seen. And the implications are massive. What kind of biosignatures we should look for has been a topic of heated discussion among astrobiologists for decades. For a long time, oxygen was thought to be the gold standard. But now we know that photodissociation makes oxygen appear without life. There are mixed feelings about methane. DMS, though, it's a very uncommon type of chemical that is usually only found when there is life present. K218b would be the first world with a gas that likely comes from living things if the DMS discovery is correct. Even though it's not proof, it's the best we've ever had. What kind of life could survive in a hydrogen-dominated sky? Could it be floating microorganisms like Earth's airborne microbes? Could it live at the ocean-atmosphere boundary, feeding on dissolved nutrients and releasing sulfur gases like exhaust fumes? Would it be carbon-based? Would it be DNA-based? Or would it be something entirely new? The 99.7% probability, what that actually means scientifically. Headlines like 99.7% chance of life on K218b sound like they belong in a science fiction book. It's almost certain, like the chances of flipping a coin 5 times in a row and getting heads each time. Scientists aren't just making things sound confident when they say there's a 99.7% chance that biosignatures on K218b are real. We got that number from careful statistical modeling, using a method called Bayesian reasoning. To know what this claim means and doesn't mean, we need to look into how that number was made. The data comes from transmission spectroscopy, where JWST analyzes light that passes through the planet's atmosphere as it transits its star. That light gets filtered by gases in the atmosphere, which absorb certain wavelengths. When scientists compare what they expect to see in a normal abiotic atmosphere versus what they actually see, they run simulations, millions of them, to test different combinations of gases, temperatures, pressures, and cloud cover. That's where Bayesian statistics comes in. Instead of asking, is this atmosphere unusual? Scientists ask, given the data we see, what's the probability that it came from a planet with biological activity? Bayesian models allow you to update your level of belief in a hypothesis based on new evidence. It's a powerful method because it balances both prior assumptions and real-world observations. So in the case of K218b, researchers came up with 2 main possibilities. First, the atmosphere could be shaped by non-living processes, things like chemistry, volcanoes, sunlight reactions, or geologic activity. This means all the gases we see might come from natural, non-biological sources. Second, the atmosphere might contain signs of life, with living organisms producing gases like methane, CH4, and dimethyl sulfide, also called DMS, just like microbes do on Earth. They then tested both models against the JWST data, and the biosignature model fit the observations much better. Not just slightly, it outperformed the abiotic model by a significant margin, leading to a 99.7% Bayesian posterior probability in favor of the life hypothesis given the observed spectrum. But here's the catch. 99.7% confidence does not imply 99.7% certainty that aliens exist. It means that based on the data and the models that were used, there is a 99.7% chance that the biosignature theory fits the sky better than a dead one. It's a way to check how fit a model is, not a statement of fact. To arrive at this number, scientists used what's called a nested sampling algorithm, a machine learning-aided method that combs through high-dimensional data spaces and identifies the best-fitting solutions. This process generates a posterior probability distribution, which basically ranks different hypotheses by how well they explain the data. The more a model matches the spectrum, the more likely it is to be true, at least under current assumptions. Bayesian models are only as good as the inputs you give them. And in the case of K218b, we still have limited data. We've only observed a handful of transits. Cloud coverage and atmospheric mixing could skew the spectra, and the models are based on our Earth-centric understanding of biochemistry. If life on K218b is completely alien, or if some exotic chemistry is mimicking biosignatures, the model might be fooled. Another factor that influences confidence levels is spectral noise, the unavoidable distortions in the data caused by instrumental imperfections, cosmic rays, or just statistical randomness. JWST has done an incredible job minimizing noise, but it's not zero. That's why scientists emphasize the need for repeat observations, especially over different seasons or phases of the planet's orbit. The more data we have, the better we can separate real signals from noise. So what does the 99.7% probability actually mean for the big question? Is there life on K218b? We're not sure, but we're more confident than ever before. The number doesn't prove anything on its own, but it raises the stakes. It tells scientists, this planet is weird in a lifelike way, it deserves more attention, it might be special. In science, 99.7% is a big deal. In particle physics, it's equivalent to about 3 sigma confidence, a threshold where people start to get excited, though they usually wait for 5 sigma, about 99.9999%, before calling something a discovery. In medicine, it might be enough to start a clinical trial. In astronomy, it's enough to write a headline with a big asterisk. And that asterisk is important. Because Bayesian analysis is about how well we can explain what we see, not what is ultimately true. It's possible that future data might lower the confidence level, especially if DMS turns out to be an artifact or a misidentification. But it's also possible that additional data pushes us to greater than 99.99%, transforming this hint into confirmation. Hydrogen-rich atmospheres. Can life thrive in these alien conditions? If you think of a world where people could live, it probably looks a lot like Earth, with bright skies, oxygen, and an atmosphere mostly made up of nitrogen. But K218b doesn't fit that at all. Most likely, its atmosphere is mostly hydrogen, with small amounts of methane, carbon dioxide, and water vapor. Its atmosphere does not contain nitrogen or oxygen. That might sound dangerous or unlivable to a lot of people. But the truth is even stranger. Atmospheres high in hydrogen might make it easier to find life, and might even be better for strange types of biology. What does it mean for the environment to be rich in hydrogen? In the world, hydrogen, H2, is the lightest and most common element. On a planet like K218b, it makes up most of the atmosphere's upper layers. Because of this, the air is very different from the air on Earth. The atmosphere doesn't get tight and thick because hydrogen has a light molecular weight. Instead, it expands, creating a puffy shell that goes up higher. That's important for 2 reasons: being able to live there and being able to be found. From a habitability perspective, hydrogen has often been overlooked. It's highly reactive and doesn't stick around easily on smaller planets like Earth. Our gravity isn't strong enough to hold onto it long term. But K218b is massive, about 8.6 times Earth's mass, meaning it can hold onto a thick hydrogen envelope without losing it to space. This atmosphere could help insulate the planet, keeping surface or ocean temperatures stable, especially if it's tidally locked and exposed to extreme day-night contrasts. Recent lab studies and theoretical models suggest that life could survive and even thrive in hydrogen-rich conditions. Microorganisms on Earth have been found that metabolize hydrogen directly. These hydrogenotrophs can convert hydrogen and carbon dioxide into methane or other organic compounds, the same gases JWST found in K218b's atmosphere. In other words, the basic chemical tools for life already exist in hydrogen-dominated environments. If K218b has an ocean beneath this atmosphere, and all signs point to that being possible, then it's reasonable to think that life could arise at the boundary between ocean and atmosphere, much like it did on Earth. That boundary would be rich in nutrients, warmth, and chemical gradients, all the raw materials for early microbial ecosystems. In hydrogen-rich skies, biosignature gases are easier to detect. On Earth, oxygen and nitrogen create tightly packed molecules that absorb only certain wavelengths of light. But hydrogen makes the atmosphere more transparent, especially in the infrared. This means trace gases like DMS, methane, or nitrous oxide, if present, stand out more clearly against the background. That's one reason why K218b, despite being over 700 trillion miles away, revealed so much with so little. Some people say that hydrogen atmospheres are not good for life because they are too reduced chemically, too flammable, or too unstable. But that's a view that focuses on Earth. We learn that life doesn't need conditions like those on Earth more and more. All it needs is energy, a liquid, like water, and the ability to work with organic chemistry. In places with a lot of hydrogen, complicated prebiotic chemistry can grow. This is the kind of chemistry that, in the right conditions, can make amino acids, sugars, or even simple nucleotides. For example, the famous Miller-Urey experiment, which tried to simulate early Earth's chemical environment, showed that hydrogen-rich mixtures of gases could create organic compounds when zapped with electricity. The implication? Planets like K218b could have all the ingredients for life to start from scratch. Lightning, water, hydrogen, and carbon. But what would life actually look like under a hydrogen sky? Not like us. It wouldn't breathe oxygen or rely on photosynthesis. Instead, it might live in oceanic microbial mats, feeding on chemical gradients between warm ocean water and the hydrogen-rich atmosphere. Some scientists speculate it could resemble archaea, one of the oldest and most primitive domains of life on Earth, simple, resilient, and chemically versatile. And since hydrogen is excellent at trapping heat, it may help sustain life even on the night side of a tidally locked planet. The thick atmosphere would circulate heat efficiently, preventing the ocean from freezing over. This gives life more surface area and more time to develop. Two of the most important factors for biological evolution. Another possibility is that atmospheres high in hydrogen could keep the climate from collapsing too quickly. The nitrogen-oxygen balance in Earth's atmosphere is very tight. If there is too much CO2, the planet warms up too quickly. But hydrogen atmospheres, which are more flexible and have more space, could protect against huge changes. That means the temperature will be stable for longer, which means there will be more time for life to emerge. Red dwarf radiation. Can life survive the stellar flares? K218b goes around a red dwarf star. That might sound nice, a smaller star, less heat, and more stability. But there's a catch. Stellar flares, which are caused by red stars, are well known for making planets uninhabitable. These flares are strong, unexpected, and sometimes very bad. They can hit a planet with radiation strong enough to remove its atmosphere and kill any living things on the surface. Also known as M-dwarfs, red dwarfs are the most common type of star in the Milky Way. They burn hydrogen slowly and live for trillions of years, far longer than our Sun. They're small, faint, and cool, which means their habitable zones, the sweet spot for liquid water, are very close to the star. K218b, for example, orbits its star every 33 Earth days at a distance about 1/10 that of Earth's orbit. This close proximity means it's bathed in the red dwarf's light, but also sits within striking range of any magnetic or radiation storms. Red dwarfs, especially young ones, are known to be highly active. They can release superflares, sudden outbursts of ultraviolet, UV, and X-ray radiation thousands of times more intense than anything the Sun produces. These flares can erode atmospheres, bombard planetary surfaces with deadly rays, and even sterilize the top layers of oceans. But not all red dwarfs are equally aggressive. The good news for K218b? Its host star, K218, appears to be relatively quiet for a red dwarf. It's an older mid-type M-dwarf, not a young flare star like Proxima Centauri. While it's not completely inactive, observations show that it doesn't produce frequent superflares, and its UV output is moderate compared to other stars in its class. That alone makes it much more likely that K2-18b will keep its environment fixed and be able to support complex chemistry for billions of years. That being said, we can't rule out the odd flash. The real test is whether life can remain, change, or even do well in the face of such a threat. The answer might be yes, which is a surprise. Life on Earth has changed over time to be able to live in places with a lot of radiation. Some bacteria can handle UV amounts that humans can't even begin to imagine. Others live deep underground, where the seas protect them from the sun's harmful rays. All signs point to K2-18b having a thick atmosphere. This atmosphere could act as a shield against radiation, spreading and absorbing it before it hits the ocean below. Hydrogen-rich atmospheres in particular are good at blocking UV light. Combine that with potential layers of clouds or haze, and you have an even stronger barrier. That means surface-level or subsurface organisms might never experience the full brunt of a flare. They'd live in relative peace, tucked beneath the atmospheric armor of their alien sky. If K2-18b has a global ocean, it offers the perfect refuge. Water is an excellent radiation shield. Just a few meters below the surface, UV and X-rays are almost completely absorbed. On Earth, we've found extremophiles living near hydrothermal vents, completely cut off from sunlight, thriving on chemical energy alone. If K2-18b has similar environments, it could harbor life forms that have never even seen their star. Flares aren't just dangerous, though. They can actually do interesting things with the makeup of planets. Photochemical processes can be started in the atmosphere by high-energy light. These reactions break molecules apart and make new ones. On Earth, these kinds of interactions helped make the first organic molecules, which are what life is made of. In fact, some experts say that stars need to be a little chaotic in order for life to start. If it's too quiet, you won't get the energy boost you need to start living. If it's too harsh, everything will be destroyed, just active enough to stir things up, but not so active that it turns the table over. That's where K2-18b's host star might be. There's also the possibility of magnetic fields. If K2-18b has a magnetic dynamo generated by a rotating conductive interior, it could produce a planetary magnetosphere, like Earth's. This invisible bubble deflects charged particles and shields the atmosphere from being stripped away. We don't yet know if K2-18b has such a field, but its mass and potential internal heating give it a shot. What we do know is that the conditions aren't hopeless. Red dwarfs were once considered too unstable for life, but recent discoveries, including K2-18b, are forcing a rethink. With the right combination of atmosphere, magnetic protection, and aquatic environments, planets around these stars might be more habitable than we imagined. In fact, some estimates suggest that up to 75% of potentially habitable worlds in our galaxy may orbit red dwarfs. If life can survive in these environments, even just microbes, then life could be vastly more common than we ever dared to believe. Is there an ocean? Evidence for a planet-wide liquid surface. What might be below K2-18b's atmosphere is one of the most interesting things that we don't know yet. There are many signs that this strange, faraway world might hide something amazing. A huge, deep ocean that covers the whole surface and is hidden by thick clouds and a sky full of hydrogen. First, consider the planet's size and mass. K2-18b has a radius about 2.6 times larger than Earth and a mass around 8.6 times greater. That makes it denser than a gas giant, but lighter than a rocky super-Earth. Using that mass and radius, scientists estimate its average bulk density is around 3.3 grams per cubic centimeter, right between Earth, 5.5 g per cubic centimeter, and Neptune, 1.6 g per cubic centimeter. That density suggests K2-18b is neither a solid rocky planet nor a puffy gas giant. Instead, it likely has layers, a solid or semi-solid core, a thick ocean, and a hydrogen-dominated atmosphere on top. This structure matches the profile of what scientists call a Hycean planet, a water world with a hydrogen sky. Theoretical models suggest that such planets can form when icy materials accrete beyond a star's frost line and then migrate inward. The result? A world with a deep ocean wrapped in heat-trapping gases that can keep water liquid, even far from intense sunlight. How do we know that there is liquid water, though? Take a look at the James Webb Space Telescope, JWST. It looked at K218b's atmosphere and found large amounts of water vapor, methane, and carbon dioxide, all of which strongly suggest a warm, moist climate. Also, these gases match what we'd expect to see evaporating from the surface of a warm ocean. Especially water mist would be hard to keep up unless there was a liquid storage that kept adding to it. Temperature models based on JWST data show that K218b could have surface temperatures between 0 and 30 degrees Celsius. That's 32 to 86 degrees Fahrenheit. In other words, conditions that are perfect for keeping water in a liquid state. Add in the planet's atmospheric pressure, which is expected to be higher than Earth's due to the thick hydrogen envelope, and you get a scenario where liquid water could exist over vast areas, possibly covering the entire planet. This ocean, if it exists, wouldn't be like Earth's. K218b is bigger and more massive, so its gravity is stronger, almost twice that of Earth. That means the ocean could be incredibly deep, not just a few kilometers, but possibly hundreds of kilometers thick. At those depths, water behaves differently. It forms exotic high-pressure ice layers, like Ice 6 or Ice 7, that exist only under extreme compression. So while the upper part of the ocean may be liquid, deeper layers could be solid. Not because they're cold, but because they're under crushing pressure. There may be a huge, warm, steady body of water above that ice, where the ocean meets the atmosphere, and that is the perfect place for life to grow. Life would be able to survive in such an ocean without sunshine. On Earth, ecosystems around geothermal vents deep in the seas depend on chemosynthesis, which is when living things get energy by breaking down chemicals instead of light. The water on K218b might be full of similar living things that eat hydrogen, methane, and chemicals that leak out of the planet's core. And because the hydrogen-rich atmosphere traps heat efficiently, the planet wouldn't need intense stellar energy to stay warm. In fact, the hydrogen blanket could help maintain consistent temperatures across the planet, even if it's tidally locked with one side always facing the star. Some simulations also suggest the presence of cloud layers high above the ocean, which would scatter starlight and help regulate the planet's climate. These clouds, composed of water droplets or hazes, could even protect the ocean from UV flares, acting like a parasol on a planetary scale. Now, what about tides? If K218b has a moon, or if the gravitational pull from its star is strong enough, the ocean could experience massive tidal forces, churning the water and possibly driving internal heat through friction. That could keep deeper layers from freezing, support ocean currents, and create a dynamic mixed environment where chemicals circulate. All good signs for life. It's important to acknowledge that we can't yet see the ocean directly. There are no images, no splashy waves, no shimmering surfaces. But the chemical fingerprint, the temperature range, the planet's density, and the atmospheric models all point to the same conclusion. K218b likely has a global ocean, hidden under miles of cloud and gas. What the planet's gravity and density tell us about its structure. Figuring out K218b's gravity and density gives us more than just numbers. It shows us how the planet is built from the inside out. This world is also different from everything else in our solar system that we know of. It's not rough like Earth. It's not a gas giant like Neptune. K218b is more of a type of world that is in the middle. These kinds of worlds are sometimes called mini-Neptunes or Hycean planets. No matter what you call it, though, its weight and bulk tell an interesting story. K218b is about 2.6 times wider than Earth and has over 8 times the mass. From this, scientists calculate its bulk density, basically how tightly its mass is packed. For comparison, Earth has a density of about 5.5 grams per cubic centimeter, That's because of its metal core and rocky surface. Neptune is much lighter, about 1.6 grams per cubic centimeter, since it's mostly gas and ice. K218b lands in the middle at around 3.3 grams per cubic centimeter. That means it's not just rock, and it's not just gas either. Scientists think it has layers, maybe a rocky or metal core, a thick layer of high-pressure water, possibly liquid or supercritical, and a top layer of hydrogen and helium gas. Now let's look at gravity. Since the planet is over 8 times heavier but only 2.6 times bigger, its gravity is stronger, about 1.3 to 1.5 times that of Earth. So if you weigh 150 pounds here, you'd feel like you weigh over 200 pounds on K218b, if there was even a solid surface to stand on, which there probably isn't. That added gravity compresses the interior, increasing pressure at depth and dramatically changing how materials behave. For example, water deep inside K218b wouldn't stay in its familiar liquid form. Under extreme pressure, water can become supercritical, a weird state of matter that's neither a liquid nor a gas. Go deeper still, and the water becomes solid again, but not ice as you know it. We're talking about Ice 7 or Ice X, exotic phases of ice that exist only under megabar pressures. These layers matter because they determine what kinds of environments life might inhabit. At the top, you have a hydrogen-rich atmosphere, thin and extended, shaped by the planet's low density and powerful gravity. This layer likely contains clouds, haze, and all the molecules JWST detected: water vapor, methane, carbon dioxide, and potentially dimethyl sulfide, DMS. It's in this region that biosignatures are easiest to spot, since the atmosphere stretches far into space, allowing starlight to pass through and get tagged by atmospheric chemicals during transits. Below that atmosphere lies what many scientists believe to be a massive water layer. This could be a super deep ocean, perhaps hundreds of kilometers thick, far deeper than anything on Earth. It might be warm, due to both greenhouse heating from the hydrogen envelope and tidal forces from the star. If so, the ocean could be fully liquid at the top and slowly transition to supercritical fluid, and finally exotic ice as pressure increases with depth. This layer could be the most biologically active region, an ocean-atmosphere interface where gases dissolve, nutrients circulate, and chemical gradients provide the energy that life might use to survive. If hydrothermal activity exists on the rocky core below, it could feed microbial ecosystems like the ones around Earth's deep-sea vents. The core is the last part. It is probably made up of silicates, iron, or a mix of strong elements. This dense center area might not be directly available to life, but it is very important. Its heat, which could come from radioactive decay or the energy left over from creation, could cause circulation in the water layer above it. And that heat could keep the planet's core from freezing solid, which would help keep things stable in the long term. The planet's gravity and density also tell us that K218b must have kept a lot of its atmosphere for billions of years. Star wind and radiation can quickly remove hydrogen from the atmospheres of smaller worlds. But K218b stays in place thanks to its gravity, even when its red dwarf star lights up every once in a while. That's why we can still detect its primordial gases, the same light elements it formed with. This gravity also implies that if anything lives on K218b, it evolved under conditions very different from Earth. Creatures, if they exist, might be squat, strong and dense, adapted to the crushing pressure of high gravity and deep oceans. Floating microorganisms might be favored over tall, structured life forms. There wouldn't be birds or trees here, but there might be plankton, microbial mats, or even alien equivalents of jellyfish drifting in the chemical soup. Temperature and pressure. Can liquid water exist at the surface? One component, liquid water, consistently ranks first when it comes to habitability. But just because there is water mist in the air doesn't mean there is water on the ground. For that to happen, a planet needs the right mix of warmth and pressure, which is not easy to find on a strange world like K218b. So, does K218b have the right conditions for liquid water? Based on how far it is from its red dwarf star and how much energy it gets, scientists estimate its temperature is somewhere between 250 to 300 Kelvin. That's about -9 to 27 degrees Celsius or 15 to 80 degrees Fahrenheit. That temperature range falls right in the zone where water could stay liquid, if the pressure is also right. So yes, under the right conditions, K2-18b could potentially have liquid water on or near its surface. This relatively mild temperature is especially remarkable when you consider how close the planet is to its host star. Just 0.15 AU, or about 1/7 the Earth-Sun distance. Normally, that would be scorchingly hot. But K2-18 is a cool, dim red dwarf, so the planet doesn't get fried. Instead, it orbits in a sweet spot where the light is gentle but consistent, and where the energy input might just be enough to warm oceans or water-rich layers without boiling them away. Now let's talk about pressure, the second key factor for liquid water. On K2-18b, the pressure is expected to be much higher than on Earth. That's because of two main reasons. First, the planet's stronger gravity squeezes everything down more tightly. Gases, liquids, everything gets compressed. Second, K2-18b has a thick atmosphere full of hydrogen, which adds tons of weight on top of any possible ocean layer below. Together, this creates an environment where high pressure could keep water in a liquid or even supercritical state, even at higher temperatures. Scientists estimate that surface pressures on K2-18b could range from a few hundred bars up to thousands of bars. For reference, Earth's surface pressure is 1 bar. At the bottom of Earth's Mariana Trench, pressure reaches about 1,100 bars. K2-18b's ocean, if it exists, could be under even more extreme pressure depending on how deep it is and how thick the atmosphere is. The good news: water stays liquid under high pressure, even at higher temperatures. In fact, the pressure can push the boiling point of water up dramatically. At 100 bars, water won't boil until it hits about 311 degrees Celsius, 592 degrees Fahrenheit. So even if K2-18b is slightly warmer than Earth, the elevated pressure would keep the water stable and liquid. But pressure and temperature don't just affect the water. They also affect the atmosphere's chemistry and structure. At high pressures, certain gases behave differently. Methane and carbon dioxide can dissolve into water more easily, altering the ocean's acidity and potential chemistry for life. The water may also enter a supercritical state near the base of the ocean, where it behaves like a gas and a liquid simultaneously. No surface tension, no bubbles, just an ultra-dense fluid. That sounds exotic, but supercritical water can support complex chemical reactions, including those needed for organic molecule formation. In other words, what would the surface look like? It's not likely that K2-18b has a solid surface in the usual sense. Most models say it's a world with a lot of water, and a layer of strange ice or silicate rock might be deep below a huge ocean. Depending on how much haze is there, the point where liquid water meets the air could be a warm ocean surface or a soup covered in clouds and fog. The Earth may be covered in thick clouds of hydrogen that reflect light and keep temperature changes from being too noticeable. Below, layers of liquid water are heated by sunshine, geothermal energy, or both. That interface between ocean and atmosphere is key. It's where light, heat, gas, and liquid all meet. It's also the zone where biosignatures like dimethyl sulfide, DMS, could be produced and released into the air. If microbial life exists, it would likely inhabit this turbulent boundary layer, thriving on the temperature gradients, dissolved gases, and access to both light and nutrients. What if K2-18b is tidally locked, with one side always facing the star and the other in permanent darkness? Would that ruin the chance for liquid water? Not necessarily. A thick atmosphere like K2-18b's can redistribute heat efficiently, especially with hydrogen, which is excellent at conducting thermal energy. Climate models suggest the planet could maintain global average temperatures within the habitable range, even if one side is baked and the other frozen. Ocean currents, wind patterns, and atmospheric circulation would smooth out the extremes. The result? A stable thermal environment where liquid water could persist for billions of years. Even if the top layer freezes, water might remain liquid below, like on Europa or Enceladus. With enough internal heating, possibly from radioactive decay or tidal forces, the ocean could be warm at depth, creating an environment for life away from starlight, just like Earth's deep-sea vent systems. In that case, what do the pressure and temps tell us? They say that K218b probably has all the right conditions for liquid water to exist, not just frozen in ice or floating as mist, but in huge amounts, sitting under the clouds and staying stable over geological ages. It's not just, would you boil in a second? Or, could it rain there? It's about long-term balance, a world that keeps its water, keeps its heat in check, and stays calm enough for life to start, change, and maybe even grow. Methane plus carbon dioxide plus DMS, a signature trio of life. Astronomers used the James Webb Space Telescope to look at K218b's atmosphere and found more than one interesting gas. 3 molecules, methane, CH4, carbon dioxide, CO2, and maybe dimethyl sulfide, DMS, were found together. Together, they make one of the greatest biosignature signs ever seen. This mix says life on Earth, and the fact that it exists on an asteroid makes astrobiologists very serious, very excited, and very careful. Methane is a colorless, odorless hydrocarbon that plays a major role in Earth's atmosphere, and it's a known byproduct of biological activity. On Earth, over 90% of atmospheric methane comes from biological sources. Microbes in wetlands, cows digesting food, rice paddies, landfills, and more. There are abiotic sources too, like volcanism or hydrothermal vents, but these typically occur at much lower levels, and they don't last long in the atmosphere without being replenished. Methane is chemically unstable in most atmospheres. Sunlight breaks it down through photochemical reactions. If you see methane in a planet's atmosphere, especially alongside oxygen or CO2, something has to be replenishing it, fast. On K218b, the detected levels of methane are higher than expected from purely geological models, suggesting an active source. It might be life. It might be something we don't yet understand. But it's definitely something. Carbon dioxide is a common gas in planetary atmospheres. Venus has tons of it, Mars too. But its role in this trio is just as important because carbon dioxide is a stabilizer. It tells us about a planet's carbon cycle, how carbon moves between the surface, atmosphere, and interior. In biosignature analysis, CO2 is often used as a control gas. When combined with methane, CO2 helps scientists determine whether the atmosphere is in a state of chemical disequilibrium. In simpler terms, if two gases shouldn't naturally exist together for long, but they do, it implies something is actively maintaining them, possibly life. That's what we see on Earth. CH4 and CO2 coexist, despite constantly reacting with each other. The only reason they both persist? Living organisms are pumping them out non-stop. If K218b has a similar balance, it hints at a dynamic atmospheric system, possibly with biological processes involved. Then there's DMS, or dimethyl sulfur. This is the wild card. This gas is mostly made by marine phytoplankton, which are tiny creatures that live in the water and release it as part of their metabolism. Volcanism, photochemistry, or air chemistry are the only known abiotic processes that can keep DMS levels high enough to be detected in Earth-like settings. When JWST found a weak but steady signal that matched DMS, it was a shocking discovery. More measurements are needed to be sure that the signal is real, but if it is, we might be seeing the breath of life on another world. DMS is more than just a life tracker. It helps keep the Earth's temperature stable by encouraging clouds to form over the seas. If it's on K218b, it might be doing the same thing, making clouds, keeping the temperature stable, and leaving a mark that we can see from 120 light-years away. Individually, methane or carbon dioxide or even DMS might be explained away by exotic chemistry or fluke processes. But together, that's where the magic happens. This trio, CH4, CO2, and DMS, exists in a finely tuned thermodynamic imbalance. In a lifeless world, these gases would destroy each other over time. Methane would react with oxygen or hydroxyl radicals. DMS would break down quickly under UV radiation. CO2 would build up while methane vanished. The fact that all three are present and relatively stable means they must be getting replenished continuously. This doesn't mean there's alien plankton swirling in K218b's ocean. It doesn't mean there's a biosphere. There are still alternative explanations. Photochemistry in a hydrogen-rich atmosphere is tricky. We might be seeing overlapping absorption features or unknown sulfur chemistry mimicking DMS. And JWST, as sensitive as it is, has only observed a few transits. The signal needs to be confirmed. Also, life on Earth makes these gases, but that's Earth life. We don't know what alien life might do or what entirely abiotic processes might produce under the extreme pressures and temperatures of K218b. That's why scientists remain cautious. The term biosignature candidate is being used carefully, not proof of life. But make no mistake, this trio of gases is the closest thing we've ever seen to the chemical fingerprints of life on another planet. How K218b compares to Earth-like exoplanets. Some people say that K218b is one of the best places to look for alien life, but make no mistake, it's not like Earth. You wouldn't last a second on its surface because it's not hard and doesn't have air. But K218b might be a better place to look for life than the so-called Earth twins that have been in the news a lot, like Proxima b or Kepler. 452b. K218b is much larger than Earth. With a radius about 2.6 times greater and a mass roughly 8.6 times higher, it falls into a category of planets we call mini-Neptunes, larger than terrestrial worlds, smaller than gas giants. Earth-like exoplanets, by contrast, are roughly Earth-sized with similar compositions. Rocky crusts, thin atmospheres, and, ideally, surface water. Proxima b, for instance, is very close to Earth in size and orbits within the habitable zone of its star, the red dwarf Proxima Centauri. But its parent star is extremely active, bombarding the planet with radiation and possibly stripping away its atmosphere. In fact, many Earth-sized exoplanets found around red dwarfs suffer from this issue. They may be in the habitable zone in terms of temperature, but they've likely lost their atmospheres entirely, leaving them dry, frozen, and dead. K218b, on the other hand, has managed to hold on to its thick hydrogen-rich envelope. That makes it completely un-Earth-like. We don't have anything like it in our solar system, but that thick atmosphere may be exactly why it's so interesting. It protects the planet's surface or ocean from stellar flares. It traps heat, creating a stable environment. And it allows spectral biosignatures to rise up and be detected by telescopes like JWST. Then there's the question of detectability. Earth-sized planets are hard to study. Their thin atmospheres produce weak signals during transits, often drowned out by noise. That's one reason we know relatively little about the atmospheres of planets like Kepler 186f or TRAPPIST-1d. They're great theoretical homes for life, but we can't see inside their atmospheres clearly enough to confirm much. K218b is different. Its larger size and puffier atmosphere make it perfect for transmission spectroscopy. As starlight passes through the atmosphere, it carries a clear chemical imprint, one we've already used to detect water vapor, methane, CO2, and possibly even DMS. In this sense, K218b is one of the most transparent windows we've ever had into an alien world's chemistry. Kepler 452b was once called Earth's cousin, but it's actually about 60% bigger than Earth and might have a thick atmosphere that traps heat, possibly causing a runaway greenhouse effect, kind of like Venus. Scientists still aren't sure how hot it really is. K218b, on the other hand, is thought to have surface or ocean temperatures between 0 and 30 degrees Celsius, that's 32 to 86 degrees Fahrenheit. In other words, right in the sweet spot for liquid water. Even though it orbits much closer to its star, the star is a cool red dwarf, and K218b's thick atmosphere helps trap just the right amount of heat, keeping things nice and temperate. What about Proxima b again? While it's closer to Earth in size and orbit, its host star is violent, blasting it with frequent UV and X-ray flares that could destroy any surface habitability. In contrast, K218b's star is relatively quiet. It does have some flare activity, but nothing like the extreme radiation environment seen around many red dwarfs. So while Proxima b might look more like Earth, K218b might behave more like a habitable world. Then there's the question of how life might really work. Planets that look like Earth might look familiar, but they might not have any life on them. Microbes don't always do well in thin atmospheres and on hard surfaces, especially if they can't get away from radiation or find safe water. Even though we can't picture living there, planets in the ocean like K218b might be better places for life to start and grow because they are more chemically rich, have stable temperatures, and last longer. Why is DMS so rare outside Earth? Dimethyl sulfide, DMS, is different from other gases that scientists have thought might be biosignatures because it can only be found in living things on Earth. It is not only very rare in the world, but also in every non-living thing we know of. Because of this, its possible discovery on K218b is one of the most amazing events in the search for life beyond Earth. So, what exactly is DMS? Chemically, it's a volatile organic sulfur compound with the formula CH32S. It's a gas at room temperature, slightly flammable, and has a strong sulfuric odor, often described as smelling like the sea. That's no coincidence, because on Earth, DMS is primarily produced by phytoplankton, microscopic marine organisms that live near the surface of the ocean. These plankton synthesize a compound called dimethylsulfoniopropionic, DMSP, which acts as an internal salt regulator. When plankton die, break apart, or get eaten, DMSP breaks down into DMS, which then escapes into the atmosphere. There, it plays a surprisingly important role in Earth's climate system by seeding clouds, regulating solar radiation, and influencing weather patterns over oceans. There are no significant non-biological sources of DMS on Earth. Volcanic activity doesn't produce it. Lightning doesn't synthesize it. Even under extreme lab conditions, DMS is hard to generate abiotically. This makes it incredibly special. Unlike methane or oxygen, which can come from life or geology, DMS is almost entirely biogenic. This is what makes the possible detection of DMS on K218b such a huge deal. If confirmed, it would mark the first time in history that a gas linked only to life on Earth has been detected in the atmosphere of another planet. Could anything besides life create DMS on K218b? So far, we don't know of any convincing abiotic pathways. You'd need a specific combination of reduced sulfur, organic carbon chains, low oxygen conditions, and delicate catalytic steps, all under precisely controlled pressure and temperature. And even then, production would likely be so low that we'd never detect it from Earth. Some models have proposed that photochemistry in hydrogen-rich atmospheres could create DMS under exotic conditions. But those ideas remain theoretical and unproven, and none of them predict the quantity of DMS that JWST may have seen, especially not alongside methane, carbon dioxide, and water vapor. That context really matters. Finding DMS by itself would already be exciting, but finding DMS alongside other key gases, in the right amounts and at the right temperatures, starts to look like a biological signature. It's like a chemical clue that, here on Earth, only shows up where life is active and thriving. So why don't we see DMS anywhere else in our solar system? Scientists have checked. They've studied the atmospheres of Venus, Mars, Titan, and even comets, searching for sulfur-based gases. But DMS, it's never been found. Not even on Io, Jupiter's volcanic moon, which is full of sulfur. This tells us two important things. First, DMS is fragile. Sunlight and oxygen can easily break it down, so it won't stick around unless something keeps making more of it. Second, DMS is extremely rare, or maybe it only exists in places where life is present. So far, Earth is the only place in the entire universe where DMS is found. And it's tied to plankton, oceans, and ecosystems that exchange gas with the atmosphere. Exactly the kind of system that K218b might possess. That doesn't mean DMS on K218b proves life exists there, but it does mean that our best explanation for DMS is biology. And that's why the scientific community is treating the signal with so much excitement and so much caution. Also, there's the matter of how reliable the discovery is. Even though JWST's detectors are very sensitive, the infrared tracks we're talking about are billions of miles away and hidden by layers of atmospheric noise. Another chemical might be acting like DMS, or the discovery could have been a mistake in the way the data was processed. That's why the next few years of transits will be very important for proof. The search for DMS is pushing the limits of what we know about sulfur chemistry, the atmospheres of other planets, and biosignature science, even if the detection turns out to be wrong. Scientists in fields like chemistry, astronomy, and space exploration are being pushed to think about what gases are truly unique to life. Which signal can we trust to work everywhere? Atmospheric modeling: how scientists simulate alien skies. Scientists don't look through a space camera and read labels in the clouds when they say they can find molecules like methane or dimethyl sulfide on K218b. They are working with spectra, which are long, complicated lines of light data. They show us how starlight reacts with the atmosphere of a planet as it passes through during a transit. But those trends aren't easy to understand. There's a lot of noise and mess in them. Models of the atmospheres of exoplanets are one of the most advanced and important tools used by scholars to make sense of all this. It begins with radiative transfer models. These are highly detailed simulations that track how light moves through a medium, in this case, a planet's atmosphere. Different gases absorb light at different wavelengths. For example, methane absorbs strongly around 3.3 microns in the infrared, while water vapor dominates near 1.4 and 1.9 microns. DMS has its own fingerprint, faint but detectable, in specific bands. The model shines simulated starlight through different combinations of gases, temperatures, pressures, and cloud layers, and compares the resulting spectrum to what JWST actually observed. It's a giant game of matching patterns. The better the simulated spectrum fits the real data, the more likely that particular atmospheric composition is correct. But it's not just about gases. The models must also account for temperature gradients, pressure profiles, altitude-dependent chemical interactions, aerosols, and cloud opacity. For K218b, these variables are even more complex due to its hydrogen-rich atmosphere and likely thick cloud cover. The models must simulate an atmosphere vastly different from Earth's, with potential supercritical fluids and alien chemistry. This is where Bayesian statistics come in. Scientists use these statistical tools to test millions of different atmospheric combinations, comparing how well each one matches the data. The model that best explains the spectral features is ranked highest, not because it's guaranteed to be correct, but because it's the most probable explanation based on what we currently know. This process is called retrieval modeling, and it's extremely demanding. Some of the simulations can take weeks to run. Scientists often rely on supercomputers or cloud-based platforms to handle the massive number of calculations needed. They test thousands of possible atmospheric scenarios, each with slightly different conditions, to see which one best matches the real data. For example, they might explore what happens if dimethyl sulfide is removed, but methane and carbon dioxide are left in. They might ask whether the observed spectrum could still be explained without any life involved at all. Or they might test what changes occur if the clouds are thicker, or if the atmosphere contains more nitrogen than expected. Each version helps narrow down the possibilities and brings them closer to understanding what's really happening on the planet. Each of these scenarios produces a new spectrum, which is then compared to the observed one. The more variables you include, the more complex the model becomes, but also the more accurate. Dealing with degeneracy, which is when different mixes of gases produce similar spectral patterns, is one of the hardest parts of modeling the atmosphere. To give you an idea, methane and carbon dioxide mixed together might look like methane with less clouds. The profile of DMS could be mistaken for that of a rare sulfur molecule that we haven't yet categorized. That's why trust numbers are so important, like the 99.7% chance we talked about earlier. They give a number that shows how much better one type is than the others. There's also the issue of clouds and haze, which can obscure or flatten spectral features. A thick cloud deck can mute gas absorption lines, making it harder to detect small molecules. K218b likely has a cloud layer, possibly composed of water droplets, hydrocarbon hazes, or even exotic ices, and that layer could dramatically affect the light passing through. That's why models must also simulate how clouds scatter and absorb light at different altitudes and wavelengths. To ensure their models are reliable, scientists cross-check with lab data. Every gas used in these simulations has been studied on Earth, its absorption spectrum recorded under various pressures and temperatures. For more exotic molecules, scientists rely on quantum chemistry calculations to predict how they behave under conditions we can't easily recreate. It's really amazing that all of this work, millions of models, weeks of computer time, and complicated chemistry, is done to figure out what a few dips in starlight mean. But those tiny dips hold a lot of information. With them, experts can figure out not only what gases are there, but also how much of them there are, where they are, and how hot or cold it is. And the end result is amazing. We know that K218b might have liquid water, methane, CO2, and maybe even DMS just from looking at it without ever taking a straight picture of it. Could the DMS detection be a false signal? The most exciting three letters in the search for life beyond Earth are DMS, sulfide of dimethyl, possibly found in the atmosphere of K218b, a gas that, on Earth, is mostly made by sea life and isn't thought to come from any geological or photochemical processes in big amounts. It's exciting, but it also comes with a heavy burden. What if we're wrong? Could the K218b DMS signal be a fake alarm? First, let us talk about how JWST finds chemicals such as DMS. It doesn't really measure gas, it checks the light. Starlight gets through K218b's atmosphere when it moves in front of its mother star. Astronomers study the pattern of colors that different gases receive. This pattern is called a spectrum. In the infrared, DMS has a clear set of faint absorption features. But so do other molecules, and some of them can touch each other. So that's the first problem: spectral confusion. The DMS signal that was seen could be a mix of other gases, especially if the atmosphere contains chemicals that haven't been studied much in places with a lot of hydrogen. For instance, at the right temperature and pressure, certain gases that contain sulfur or even long-chain hydrocarbons might show similar patterns. Our collections of molecular spectra, such as Hytran and Exomol, are always getting better, but they're still not full for molecules that don't exist on Earth. Then there's instrumental noise. No telescope is perfect, and even JWST, with its unparalleled sensitivity, has noise in its data. Cosmic rays, detector sensitivity variations, and thermal fluctuations can all introduce tiny artifacts. These artifacts can appear as blips in the spectrum, and if a blip happens to occur where DMS would absorb, it might be misinterpreted as a real detection. JWST uses powerful filters and calibration methods to reduce these risks, but statistical fluctuations are always possible. When you're working with extremely faint signals, as small as 1 part in a million, even a little misalignment can produce a false positive. Another problem is low signal-to-noise ratio, SNR. The possible DMS detection came from just a few transits of K218b. That means we only have a limited amount of light, a small window of data, and just a handful of opportunities to capture the full spectral picture. To be confident that DMS is really present, astronomers need multiple consistent detections across many transits, ideally using different instruments and wavelengths. Bayesian modeling, which was used to estimate a 99.7% confidence level for the biosignature hypothesis, is only as strong as its assumptions. If there's an unknown abiotic process producing something that mimics DMS, or if the model assumes a cloud layer that doesn't actually exist, the results could be misleading. In other words, the models might be overfitting, finding patterns that match DMS because that's what they're trained to expect. We also need to consider observational bias. Scientists know that DMS is a powerful biosignature, so they look for it eagerly. But the more eagerly you search, the easier it is to overinterpret marginal signals. This doesn't mean the researchers are being dishonest, just human. That's why peer review, independent analyses, and repeat observations are so essential in cases like this. Furthermore, it is the planetary context. The atmosphere of K2-18b is full of hydrogen. Under strong ultraviolet light, DMS is known to be fragile and can break down quickly if it isn't constantly replaced. If DMS is really there, we should also see SO2 or other sulfur oxides that are made when DMS breaks down. But these haven't been clearly found yet. That difference in power could mean that the DMS signal is either wrongly identified or happening in a way that is very different from what we see on Earth. To make things even more difficult, K2-18b is not like any other planet in our solar system. It's not hard like Earth, not cold like Europa, and not gassy like Neptune. This world is somewhere in the middle. It might be a Hycean world, covered in mist and having deep seas and high pressures. We may not fully understand the strange effects that the science of such a world may give us yet. DMS-like molecules might form on their own in places we haven't looked into in great detail. So is the DMS detection real? Maybe. It fits the data better than other models, for now. But it's not a slam dunk. The signal is tentative, indirect, and open to multiple interpretations. That's why upcoming transits of K2-18b, scheduled through 2026 and beyond, are so crucial. With more data, scientists can increase the signal-to-noise ratio, refine their models, and verify whether the DMS-like feature persists or vanishes under closer scrutiny. Future JWST observations. What comes next for K2-18b? K2-18b became a news story overnight when the James Webb Space Telescope made its first set of images. Steamy water, propane, it's carbon dioxide, it could even be dimethyl sulfur. We had a good option for the first time for a world outside of our solar system that could support life. But science doesn't depend on news stories, it depends on proof. And right now, scientists are getting ready for a second set of readings that could either prove the first ones right or seriously question them. So what's next for K2-18b? More transits, more data, better models. The James Webb Space Telescope is scheduled to revisit the planet multiple times between 2026 and 2027, carefully watching as it again passes in front of its star. Each transit provides a new opportunity to gather more light, more infrared spectra, and more atmospheric signatures. With each pass, the signal-to-noise ratio increases, helping to separate real signals from possible artifacts or statistical flukes. The key goal for these future transits is confirmation of the biosignature candidates. The DMS signal, for example, is still considered tentative. It was visible in the data, but right at the edge of detectability. In future transits, JWST will aim its NARSPEC and NIRIS instruments again, this time with longer exposure times, refined calibration methods, and improved targeting precision. If DMS shows up again, and with more clarity, it becomes much harder to dismiss. These new observations will also help confirm and refine the abundance of methane, carbon dioxide, and water vapor. Right now, the best-fitting atmospheric models suggest K2-18b has a hydrogen-rich envelope with trace gases that resemble Earth's life-linked chemistry. But the current uncertainty bars are still wide. A better dataset will help narrow down how much of each gas is actually present, and whether they exist in combinations that truly defy abiotic explanation. The structure of the clouds will also get a lot of attention. The location and makeup of cloud layers is one of the most unclear parts of the present models. It can be hard to tell the difference between fumes like DMS and sulfur dioxide when there are clouds and hazes around. With longer bands that can get through clouds better, JWST's instruments can look deeper into the atmosphere and get a better picture of what's below. Astronomers are also hoping to map vertical layering in K218b's atmosphere. That means determining whether certain gases are more concentrated at specific altitudes, a key sign of atmospheric dynamics and potential biological processes. For instance, if methane is found only near the ocean-atmosphere interface, it could point toward active biological release rather than uniform distribution from geologic sources. Other observatories will play supporting roles. The Hubble Space Telescope may contribute with UV monitoring of the host star K218. That helps scientists understand how much radiation pressure and stellar activity the planet's atmosphere is exposed to, which is essential for calculating atmospheric stability and biosignature lifespans. The Very Large Telescope, VLT, and other ground-based observatories may also monitor K218's brightness and variability. While they can't resolve the planet's atmosphere directly, they can provide essential background data, like whether the star is entering a more active phase, or if the photometric baseline is shifting. Research teams on Earth are working hard to recreate K218b's atmosphere in lab simulations. Using high-pressure chambers and chemical reactors, they're testing how various gases behave under High-Cean conditions, how DMS breaks down, how methane and CO2 interact, and whether any exotic processes could produce similar spectral fingerprints. These experiments will feed back into the modeling efforts, helping to eliminate false positives and sharpen predictions for future transits. Beyond JWST, scientists are already planning for the next wave of telescopes, such as LUVOIR and HABEX, which are still being built. In the future, these telescopes will have spectrometers that are even more powerful and direct imaging tools that could take real shots of exoplanets like K218b. That won't happen for at least 10 years, but the results they find now will help them plan their journey, choose targets, and calibrate their instruments. In the meantime, one idea for improving JWST is to make its optical features better for studying biomarkers. Scientists could make a very detailed chemical map of the planet's atmosphere gas by gas and layer by layer if they spent more time observing K218b. Clouds, haze, and skies, what the planet might actually look like. If you could stand on K218b and look up, assuming you didn't fall over from its weight or drown in its hydrogen-rich air, what would you see? The truth is, we don't know for sure. But based on current models and the latest James Webb Space Telescope data, we can make scientifically grounded guesses about what the skies of K218b might look like, and they're likely to be as alien as they are beautiful. Let's start with the atmosphere's composition. We know it's dominated by hydrogen and helium, with trace amounts of water vapor, methane, carbon dioxide, and possibly dimethyl sulfide. These gases behave differently from Earth's nitrogen-oxygen mix, especially when it comes to how they scatter light. On Earth, our blue sky comes from Rayleigh scattering. Shorter, bluer wavelengths of sunlight get scattered more effectively by tiny gas molecules. Hydrogen, being the lightest gas, can also cause Rayleigh scattering, but its effect is more subtle and diffuse. That means the skies of K218b could be pale blue, hazy grey, or even greenish, depending on the exact gas mix and the altitude you're looking from. But what really changes the game is clouds, and there are probably a lot of them. Based on spectral analysis, scientists believe K218b has a thick cloud deck, possibly composed of water droplets, photochemical hazes, or even hydrocarbon aerosols. These clouds could form in layers, much like those on Jupiter and Saturn, with the upper layer made of lighter compounds and the lower layer composed of heavier, moisture-rich condensates. The clouds may be multi-tiered, persistent, and highly reflective, which affects both the light we see from the planet and the temperature dynamics beneath. This cloud cover could be oppressive and thick, blocking out direct starlight and creating a perpetual twilight gloom below. Or it might break occasionally, revealing shafts of dim red-orange light from its red dwarf sun, K218. That sun is cooler and redder than our own, so the daylight on K218b wouldn't be bright yellow like Earth's, but more like a deep copper glow, filtered through haze and vapor. There is strong proof that there might be a global ocean, and the view from just above the top could be out of this world. Imagine a dark, shiny sea that goes on forever in every direction, with clouds the color of dull metal covering the sky. Lightning flashes could sometimes tear across the sky, lighting up clouds of floating vapor. No land, not any trees. There is no sunlight as we know it, just a never-ending ocean under a stormy sky of hydrogen. The haze is another wild card. Some exoplanets, like Titan in our solar system, are wrapped in photochemical smog, a result of UV light from the star interacting with methane. On K218b, a similar process could produce orange or brownish haze particles, suspended in the upper atmosphere. These could flatten the spectral features we observe and mute surface colors from space. From the inside, they might create a murky golden ceiling, blocking most of the red dwarf's light from reaching the ocean below. What about the weather? A planet that is tidally locked, meaning that one side is always facing its star and the other side is always in the dark, is likely what makes the strong winds and extreme weather systems happen. There could be megastorms raging at the edge of day and night, and clouds moving across the Earth at hundreds of kilometers per hour. Heat differences and deep convective layers could cause lightning, temperature updrafts, and maybe even storms from other planets. On the dark side of the planet, the clouds might thin. The ocean could be calm, reflecting a black sky peppered with stars, but with no moon to cast shadows. The contrast between day and night sides, and the weather generated in between, could make K218b's climate more dynamic than anything on Earth. Back in space, K218b would not be blue like Earth or brown like Mars. With its reflective haze and thick cloud tops, it might appear pale white, greyish, or even pink-tinged, especially when illuminated by the red hue of its star. The hydrogen-rich atmosphere would glow softly in infrared, making it look eerily ghost-like in thermal wavelengths. Is it tidally locked? Climate simulations of a split-day planet. K218b circles its red dwarf star from a very close distance, only 0.15 astronomical units, which is about an eighth of the distance between Earth and the Sun. Since K218b has a very tight orbit and is a small cool star, it makes sense to ask if it is tidally locked. In other words, does one side of the world always face its star and enjoy perpetual sunshine, while the other side always experiences perpetual darkness? It's a common phenomenon for exoplanets orbiting red dwarfs. In fact, most close-in planets around these stars are expected to become tidally locked over time due to gravitational interactions. When a planet orbits so near its star, the star's gravity exerts a torque on it, slowing its rotation until it becomes synchronized, one rotation for every revolution. Just like our moon always shows the same face to Earth, a tidally locked exoplanet would do the same to its star. So, is K218b tidally locked? Probably, but not confirmed. Based on its orbital period of 33 days and its distance from the star, models strongly suggest that tidal locking is likely. The planet has had billions of years to settle into gravitational equilibrium, and red dwarf stars don't exert as much tidal stress as larger stars. But K218b's relatively high mass and close proximity make it a strong candidate. What does that mean for the environment of the Earth? At first look, tide locking seems like it would make a place impossible to live. On one side of the world, the sun never stops shining. The other fell into a deep, freezing hole. Some climate models, like K218bes, show a more positive picture. This is especially true when the atmosphere is thick and full of hydrogen. Hydrogen is very good at transporting heat. It has a low molecular weight and high thermal conductivity, which means it can even out temperature differences across the planet far better than nitrogen or oxygen. If the atmosphere is dense enough, and all data suggests that K218b's is, Then the planet can redistribute heat efficiently from the day side to the night side. This creates a relatively stable global climate, even with wildly uneven sunlight. This is the hemisphere that faces K2-18 constantly. It receives all the stellar energy and is likely the warmest region. The heat warms the hydrogen-rich atmosphere and causes convection, hot gases rising, cooler gases sinking. This drives enormous wind currents that flow from day to night, carrying heat with them. On the night side, even though there's no direct starlight, it may not be frozen. Atmospheric circulation can keep temperatures well above the freezing point of water, especially in the upper ocean layers, if the planet indeed has a global ocean. Some models even predict cloud formation at the substellar point, the point directly under the star, and rainfall in regions where warm, moist air cools and condenses. Between the day and night sides lies the terminator zone, a twilight band that encircles the planet. This region is of particular interest. It receives just enough scattered light to stay temperate, and it's where some researchers believe life might concentrate, if it exists. With a balance between heat and darkness, stable temperatures and dynamic weather, this ring of eternal dusk could be K2-18b's most habitable real estate. Then, there's the possibility of ocean currents. If K2-18b has a deep global ocean, it might experience slow-moving circulation patterns, like Earth's Gulf Stream or thermohaline currents, helping to distribute heat beneath the surface. These currents could further stabilize temperatures across the planet and maintain liquid water even in regions far from the heat of the star. Of course, tide locking can also cause extreme weather. For instance, the day side might have a lot of photochemical activity, especially near the substellar point where UV light hits the same spot over and over again. There might be clouds that act like a planetary parasol, reflecting stars and keeping things from getting too hot. If there aren't any, you could end up with masses of superheated air, jet streams, and weather systems that are unlike anything we've seen on Earth. Meanwhile, the night side could host thick clouds or frozen mists, depending on how well heat reaches that hemisphere. It's even possible that exotic ice crystals form in the upper atmosphere, falling like snow, only to evaporate before reaching the ocean. Climate simulations for K2-18b use 3D general circulation models, GCMs, similar to those used for Earth's climate studies, but adapted for hydrogen atmospheres, greater gravity, and a red dwarf's energy spectrum. These models show that even with one side of the planet never seeing sunlight, the whole world can remain habitable, especially if the atmosphere is dense and dynamic enough. Atmospheric escape. Is the hydrogen envelope stable long-term? One thing that makes K2-18b unique is its thick, hydrogen-rich atmosphere. This is also the main reason why we can tell so much about its makeup from more than 120 light-years away. But that brings up an important question. Can it keep this climate forever? Or does K2-18b's most important trait slowly escape into space? Atmospheric escape is a natural process that occurs on nearly every planet. Even Earth loses atmosphere. Tiny bits of hydrogen and helium are constantly bleeding off into space. But for some worlds, especially those close to their stars, atmospheric loss can be catastrophic, stripping a planet down to its rocky core. This is especially true for light gases like hydrogen, which have a higher tendency to reach escape velocity and drift off into space. That said, K2-18b also orbits very close to its star, just 0.15 AU, astronomical units. Close proximity to a red dwarf like K2-18 means it's constantly exposed to stellar radiation and solar wind, especially in the ultraviolet UV range. Over time, high-energy UV photons can ionize hydrogen molecules in the upper atmosphere, giving them enough energy to escape into space, a process known as photoevaporation. This process is well documented. In fact, many mini-Neptune planets that orbit close to their stars are believed to have lost most or all of their atmospheres over time, leaving behind what astronomers call stripped cores. But K2-18b seems to have held onto its thick atmosphere, which reveals two important clues. First, its hydrogen layer is surprisingly stable, at least for now, suggesting the planet's atmosphere isn't being blown away easily. Second, its host star appears to be relatively quiet, meaning it doesn't produce many strong flares or blast the planet with high levels of ultraviolet radiation. That calmer environment helps the atmosphere stay intact. Red dwarfs vary widely in behavior. Some are extremely active, producing violent solar flares that can erode atmospheres in a few million years. Others, especially older or slower rotating ones, settle down and become much gentler. K2-18 is in the second category. While not completely dormant, it doesn't emit the levels of radiation needed to rapidly blow away a hydrogen envelope as thick as K2-18b's. But the story doesn't end there. Even if the star is relatively calm, the outermost part of the atmosphere, called the exosphere, can still slowly leak into space over time. How fast this happens depends on several things. Lighter gases like hydrogen escape more easily than heavier ones. A strong magnetic field can help by deflecting the stellar wind, which would otherwise strip the atmosphere away. The temperature of the upper atmosphere also matters. Hotter gases move faster and are more likely to escape. And finally, the star's activity cycle plays a role, since even quiet stars can go through periods of higher radiation. We don't know for sure if K2-18b has a magnetic field right now, but it seems likely. With a big core and some warmth inside, it might be able to make a magnetic dynamo that helps protect the world, like how Earth's magnetic field shields us from the solar wind. Even though K2-18b has a high gravity, it would be more likely to lose its atmosphere if it doesn't have a magnetosphere. Hydrodynamic escape models are used by astronomers to make models that show how atmospheres change over time. Most theories for K2-18b say that the atmosphere will stay fixed for billions of years, mostly because of how heavy it is. Earth and Mars have smaller atmospheres and slower escape speeds than K2-18b. This means that K2-18b can lose some hydrogen gas without big problems. Even if it leaks slowly, it could keep a hydrogen-rich atmosphere for tens of billions of years, which is a very long time compared to the age of the universe right now. Planetary cooling is a different factor at play. Planets tend to lose heat over time, which makes it harder for them to support volcanic or tectonic action, and by extension, processes that might replace lost atmosphere. But once more, K2-18b's mass is on its side. It takes longer for bigger planets to cool down, and any leftover heat may keep pushing hydrogen and other gases from the inside to the outside, cancelling out the escape. Even if the hydrogen layer eventually thins out, K2-18b may not become uninhabitable. In fact, a gradual loss of hydrogen could actually make the planet more Earth-like over time, with less atmospheric pressure, less opacity, and more surface stability. This kind of natural atmospheric evolution might turn a Hycean world into a more familiar ocean planet, albeit on billion-year timelines. Comparing K2-18b to TRAPPIST-1 planets and TOI 700d. Many astrobiologists are interested in exoplanets, not just K2-18b. In the past 10 years, a number of other worlds, including the TRAPPIST-1 system and TOI 700d, have become possible places to look for life. These worlds are smaller than Earth, have more rocks, and are a better match in size. So how does K2-18b, which has a thick layer of gas around it and is very big, compare to these other stars that are said to be more like Earth? At first glance, TRAPPIST-1 planets seem like the clear winners. The TRAPPIST-1 system, located about 40 light-years away, contains 7 Earth-sized planets, at least 3 of which orbit in the habitable zone. They are roughly the size and mass of Earth, and because they orbit a red dwarf, they're easier to detect via the transit method. They quickly became front-runners in the hunt for habitable environments. TRAPPIST-1 is an extremely active star. It frequently emits powerful solar flares, including bursts of high-energy ultraviolet and X-ray radiation that can strip planetary atmospheres over time. These flares can be hundreds or even thousands of times more powerful than anything our Sun produces. Even with a magnetic field, a small Earth-like planet orbiting close to such a volatile star is at serious risk of losing its atmosphere entirely, leaving behind a cold, irradiated rock. While it orbits a red dwarf like the TRAPPIST-1 planets, its host star is quieter, older, and far less violent. It emits fewer flares and less UV radiation, dramatically improving the chance that K218b could retain its thick atmosphere. Its greater mass also gives it a stronger gravitational hold on that atmosphere, even under bombardment from stellar winds. With current technology, it's much easier to detect atmospheric gases on larger planets with extended atmospheres, like K218b. The TRAPPIST-1 planets are small and compact, with thin or non-existent atmospheres, at least as far as we can tell. Their transits block less light, and any spectral signal from their atmospheres is much weaker, making it incredibly difficult for even JWST to detect clear biosignatures. K218b, on the other hand, is a spectral dream. Its thick hydrogen-rich atmosphere is like a giant lens, absorbing and transmitting starlight in a way that leaves clear chemical fingerprints. That's how we were able to identify water vapor, methane, CO2, and possibly DMS. The very thing that makes K218 be less Earth-like, its size and atmosphere, makes it far more detectable. Now let's look at TOI 700d. It's an Earth-sized planet discovered in 2020, orbiting in the habitable zone of a red dwarf about 100 light-years away. It's received attention because it seems calm, relatively temperate, and close enough to observe with next-generation telescopes. But as of now, we know very little about its atmosphere. We haven't detected any gases, we don't know if it has water, and we don't even know if it's truly habitable, or a barren desert. Once more, K218b wins because it has more data. We are already making detailed models of its atmosphere. We have seen proof of a constant temperature profile, complex organic gases, and a liquid water cycle. On paper, TOI 700d might look more like Earth, but many people know a lot more about K218b. That makes it a lot more useful in the search for life. There's also a question of climate stability. Rocky planets like those in TRAPPIST-1 or TOI 700 systems may be prone to extreme temperature swings, especially if they've lost their atmospheres. K218b, with its thick hydrogen envelope, is much better at distributing heat. Even if it's tidally locked, models suggest the planet could maintain relatively even temperatures across its surface, especially if it hosts a deep global ocean. Some researchers believe that Hycean planets like K218b may actually be more common and more stable for life than rocky Earth-like planets. They can exist in wider orbits, are easier to detect, and can stay habitable longer due to their thermal inertia and insulating atmospheres. Obviously, that life would be very different if it exists. It was not able to take in air, it can't live on land, it could never be seen, but it might be there in the seas, in chemical processes, or in the air of other bodies. It's not about which planet is more familiar when we look at K218b, the TRAPPIST-1 planets, and TOI 700d. It's about which one gives us the best chance of finding something living. Stellar metallicity and its role in forming ocean planets. Most people think about the world when they talk about the possibility of alien life. Is there water? Does it feel like something? Are you able to live there? But there's something secret that a lot of people miss: the star itself. What it's made of, not just how hot or stable it is. In the case of K218b, the makeup of the star, especially how metallic it is, may help us figure out how such a strange world with lots of water got there. In astronomy, metals refer to anything heavier than hydrogen or helium. So elements like carbon, oxygen, iron, and silicon, the building blocks of planets, are all called metals. When a star forms, it inherits its elemental makeup from the gas cloud that birthed it. If that cloud was rich in metals, the star and its planets will be too. If it was poor in metals, the planets forming around it might look very different from what we're used to. K218, the star that hosts K218b, is a red dwarf. And red dwarfs, especially older ones, often have lower metallicity than our Sun. That's important because lower metallicity environments tend to favor the formation of planets with large gas envelopes and less dense rocky cores. Exactly the kind of structure we suspect K218b has. In other words, the star's low metallicity may have helped shape a Hycean world, a mini Neptune with a hydrogen-rich atmosphere and a global ocean beneath. That's a big deal because for a long time, planetary scientists assumed that low metal stars would be bad at forming planets. But now we're finding that they may be the perfect factories for strange, water-rich exoplanets, especially in the habitable zone. When a planet forms in a protoplanetary disk, the ratio of ice to rock in that disk depends on the temperature and chemical content of the region. In high metal environments, rocky material is more abundant, leading to Earth-like planets with solid crusts and dense iron cores. In low metal environments, volatile elements like water, methane, and ammonia are more likely to dominate, meaning more ice giants, gas dwarfs, and Hycean worlds. K218b may have formed in a region of the disk rich in icy planetesimals. These small bodies could have collided and merged, forming a large core surrounded by water and gas. Over time, this world would have accumulated a thick hydrogen envelope, locking in heat and allowing a liquid ocean to persist beneath. The low metallicity of K218 star also affects the planet's core structure. If there's less iron and rock available, the planet might lack a dense core altogether, or have a core that's surrounded by thick, high-pressure ices and liquids. This changes how heat flows through the planet, how magnetic fields are generated, if any, and even how deep oceans interact with the atmosphere. There's more to this, though. The type of biosignatures we might find is also affected by how magnetic the stars are. Life based on oxygen has been most common in metal-rich environments like ours. This includes photosynthesis, ozone, and complicated carbon cycles. But life, if it exists, may follow very different molecular rules in places with few metals. It could depend on sulfur, nitrogen, or methane instead of oxygen, and it might not have formed in small tidal ponds. Instead, it could have happened in dark, high-pressure seas under miles of hydrogen gas. This is why finding dimethyl sulfide, DMS, on K218b is so interesting. It means that life could grow in ways that are very different from how life grows on Earth. Low metal stars like K218 could be the perfect places for this to happen. It also means that if we want to find more K218b-style planets, we should start targeting low metallicity stars, especially older red dwarfs. These stars tend to host smaller, cooler planets with long lifespans, exactly the kind of environments that give life time to evolve and stabilize. This flips the traditional thinking on its head. For years we searched for Sun-like stars with Earth-like planets. But K218b shows us that the recipe for life might involve less metal, more gas, and more water. It's like cooking with different ingredients. You can still make something amazing, but the flavors will be totally new. Can we detect seasonal changes on K218b? Once you know what time it is, you can be sure that there is life on Earth. Animals move, trees grow, snow falls, and ice melts. These changes aren't just for fun, they're also hints. There may not even be a need to see aliens if we want to show that life exists on other planets. It's only necessary for the seasons to change. The question is whether we could see seasonal changes on K218b, a world more than 120 light-years away. It might not seem possible. Astronomers are already looking into ways to find yearly trends, even if they are very small, by tracking how the light from a planet changes over time. If K218b is alive, seasons could be one of the most powerful secondary signs we could ever see. It is thought that K218b is a Hycean world, which means that it has a deep ocean below a hydrogen-rich atmosphere. A red dwarf, which is smaller and less bright than our Sun, is its mother star. Even so, The world is close enough to the Sun that it gets about the same amount of warmth, which means it might be habitable. But what about seasons? On Earth, seasons are caused by our axial tilt. As we orbit the Sun, different parts of the planet receive more or less sunlight. The question is, does K218b have a tilted axis? Right now, we don't know. Measuring the axial tilt of an exoplanet is extremely difficult, especially with current instruments, but we can guess based on its likely orbital dynamics. K218b is relatively close to its star, which makes it a candidate for tidal locking, where one side always faces the star. If that's true, it might not experience seasons at all, at least not like we do. One hemisphere would be in constant daylight, the other in constant night. But if the planet isn't fully locked, or has a wobble in its spin, called obliquity, it could experience dramatic climate variations over time. The planet's atmosphere could still change over months or years, even if there were no seasons. This could happen because of biological activity, weather trends, or photochemical cycles. How then do we find that? Light curves come in. Some sunlight gets through a planet's atmosphere when it moves across its star. This lets telescopes like JWST read the planet's chemical fingerprints. We can look for changes if we do this process over and over, year after year. If K218b has microbial life, maybe in its ocean or cloud layers, that life might produce gases like methane, oxygen, or dimethyl sulfide, DMS, in varying amounts. Just like Earth's CO2 levels rise and fall with plant growth, K218b might show similar atmospheric shifts that repeat seasonally. Even non-biological features like cloud cover, haze, or ocean evaporation can change with time, especially if the planet has a dynamic climate. By monitoring these changes, astronomers can build a time-based profile, essentially a seasonal map of a planet's atmosphere. It's like getting the weather news from 120 light-years away. And we're not making this up. From space, this idea has already been tried out on Earth. Galileo once pointed its cameras at Earth from far away to see if it could find signs of life there, just like it might on an alien world. As a result, changes in gases, shadows from the seas, and shifting patterns of plants were all seen. Even from very far away, the seasons on Earth could be read. We can try that on K218b if we can find it here. Time is the hard part. To track these slow changes, JWST and future telescopes will need to collect data over and over for years. But plans are already being made for this. Scientists want to keep an eye on potential targets like K218b for a long time, checking in on them once a year to see if there are any changes. Some are even developing AI-powered pattern recognition tools that can find minute seasonal signals that the human eye might miss, the same way we forecast weather from satellite data here. There's also a chance to detect hemispheric asymmetry, where one side of the planet behaves differently than the other. This could show up as light curve variations during different orbital positions, especially if the planet has patchy clouds or regions with more biological activity. And remember, this doesn't require us to see plants or animals. A seasonal increase in something like DMS, paired with a dip in methane, could be enough to suggest life cycles are occurring, like microscopic plankton blooming and dying with ocean currents. What if it hosts subsurface life like Europa? Life doesn't always need sun. On Earth, some of the toughest ecosystems are found under thick mountains, at the bottom of the ocean, and inside deep cracks in rocks where sunshine never gets to. One of the most extreme cases is Europa, Jupiter's cold moon. Scientists think that beneath its frozen surface, there is a salty ocean. Even though Europa's ocean floor never sees light, it might be home to microbes that live on chemical processes instead of photosynthesis. What if there is life below the surface of K218b, the world 120 light-years away from Earth that we live in? When you look at K218b's structure, this question becomes even more important. It's probably a small Neptune with a thick, hydrogen-rich atmosphere that could cover the whole world. The forces would be very high if this ocean goes down hundreds of kilometers. And if things on the top are too dangerous, like from radiation, storms, or extreme weather, then life might not do well in the sky, but down below, in the darkness. The concept is not far-fetched. Scientists already suspect that Europa, Enceladus, and even Titan may host alien microbes beneath their icy crusts. They would survive not from sunlight, but from chemosynthesis, the same process used by Earth's deep-sea vent communities. Hydrothermal cracks send out hot water full of minerals from the ocean floor. These make ecosystems that are rich and spread out, where animals eat sulfur and gas instead of sunshine. K218b might have the same thing going on, but on a level we are unable to fathom. K218b's high gravity and dense atmosphere could trap heat below the surface. If it has a rocky core, as many models suggest, then tidal forces from its host star may generate internal friction, warming the ocean from below. This would be similar to how Europa stays warm. Jupiter's gravity flexes its interior like a stress ball, generating heat. If K218b's subsurface ocean is geothermally active, you could get pockets of liquid water and nutrients in total darkness. And with that combination comes the possibility of life evolving independently, completely isolated from the surface. This could be the best place to be right now. Even though K218b's outer environment is in the livable zone, it could still be dangerous. K218, the planet's red dwarf star, sometimes sends out solar flares and ultraviolet rays. That radioactivity might sometimes go up, even if the star is mostly quiet. These bursts of energy would be able to kill any microbes found on the surface. But deep below the surface, it is completely protected. If the ocean is covered by a layer of ice or high-pressure supercritical fluid, this could prevent any biosignatures from directly reaching space. That means JWST wouldn't detect these life signs through atmospheric spectroscopy. No DMS, no methane from life, nothing visible. It would look quiet, sterile, dead. But there might be a busy alien ecosystem below that layer. This brings up an irritating thought. What if K218b is full of life that we can't see? It's like trying to figure out how diverse Earth is by only smelling its atmosphere from the moon. Watching light pass through an exoplanet's atmosphere is something that aliens might do, but they might miss what's going on under our oceans. There are even models that predict false negatives, planets that seem lifeless from afar because their life is hidden underwater or beneath clouds, or doesn't produce easily detectable gases. K218b could be one of these stealth life planets. So how would we ever find out? With current technology, we probably won't. There's no way to send a probe to K218b, not without faster-than-light travel or thousands of years of patience. But we can model it. Astrobiologists are already using Earth's extreme environments as test cases. In Arctic ice cores, in deep-sea vents, and inside subglacial lakes like Lake Vostok in Antarctica, researchers have found microbial life that survives in total darkness, high pressure, and chemical-rich environments. Some labs are now recreating Haitian-like oceans, combining hydrogen, water, and mineral-rich substrates to test what kinds of Earth microbes might survive. And the results are surprising. Many simple life forms can adapt and even thrive in those exotic soups. Gravity, tides, and internal heating. Life beneath the crust? It's not what's on the top of K218b that makes it one of the most likely places for life to exist. It's what's going on deep below it. Let's talk about why it's so important for worlds like K218b to have internal warmth. The outside of a Haitian world, with its thick fog, dense hydrogen clouds, and maybe even acid rain, doesn't always look cozy. But deep below all that chaos, something else could be happening. A warm ocean below the surface that is being kept alive by forces we can't see. On Earth, we rely heavily on the sun. It drives the climate, feeds plants, and provides energy for life. But beneath our feet, there's another powerful source of energy, geothermal heating. The planet's core is still hot from its formation and radioactive decay. It powers tectonic activity, volcanic vents, and hydrothermal systems. This internal energy supports life in complete darkness, far from any solar input. Just picture this kind of setup, but much bigger. The size of K218b is about 2.6 times that of Earth and 8.6 times that of Earth's mass. That means that its inner layers are being pushed together by gravity very strongly. What if its center is made of rocks or ice? The pressure inside could keep it hot for billions of years. When you add in ocean energy, you have a recipe for deep, long-lasting warmth. Because K218b likely orbits close to its red dwarf star, it experiences strong gravitational pulls. If the orbit is slightly elliptical, the planet stretches and squeezes as it moves around the star, kind of like kneading dough. This creates friction inside the planet, which releases heat. We see this in our own solar system. Io, one of Jupiter's moons, is the most volcanically active body we know of, not because of the Sun, but because Jupiter's gravity is constantly tugging at it. The same forces could apply to K218b, warming its interior and keeping a liquid ocean layer beneath an icy or gaseous shell. A warm interior combined with a deep ocean could allow for hydrothermal vent systems on the seafloor, just like those found in Earth's deep oceans. These vents release hot, mineral-rich fluids into the water, creating energy gradients that life can exploit. On Earth, these vents support entire ecosystems with no sunlight at all. Microbes feed on chemical reactions, not photosynthesis. Then larger organisms, tube worms, clams, shrimp, feed on those microbes. It's a fully independent food chain that could easily be mirrored elsewhere in the universe. What does this mean for K218b? If there is active internal warmth and a solid core below the ocean, then it's much more likely that there is life in the deep sea. The deep ocean could be the only safe place for life to live for billions of years, especially if the top is too dangerous because of UV radiation or hydrogen-rich chemicals. Another thing we need to think about is how water might help life. Tidal forces can move the water around so it doesn't stay still. The tides help move nutrients and air around in Earth's seas. Life could benefit from the steady cycling of important chemicals if K218b's ocean is similarly dynamic, perhaps with tidal waves caused by its star or other planetary bodies in the system. K218b's density suggests it's not a gas giant like Jupiter, but it's also not a rocky Earth twin. It falls into the category of mini-Neptunes, with thick atmospheres and possibly deep liquid layers. Some of these mini-Neptunes may actually have layered structures, a rocky or metallic core, a high-pressure water layer, then a gaseous envelope. Between those layers, where temperatures and pressures are just right, you get a zone where liquid water can exist for billions of years, shielded from space and nourished from below. In this Goldilocks layer, life might evolve completely out of view, silent, unseen, and protected. That raises a challenge for our telescopes. We might never detect this hidden life because it doesn't produce gases that leak into the upper atmosphere. In fact, K218b could host the most vibrant alien biosphere in the galaxy, and we'd never know unless we could somehow dive beneath its clouds and waves. New mission concepts like the LUVOIR and JWST space telescopes may one day allow us to study exoplanet ocean dynamics and cloud layers in much greater detail. And scientists are getting better at creating models to simulate internal heating, tidal stress, and potential biological niches, all based on just a planet's mass, radius, orbit, and star type. Some of those models predict that planets like K218b are more likely to host subsurface life than rocky planets like Earth, because they stay warm longer and have larger, more stable oceans. That's a huge shift in thinking. Because there are more mini-Neptunes and icy worlds than Earth-like planets, a recent study suggested that oceans deep below the surface could be the most common place for life in the universe. Could there be a magnetic field protecting the planet? The magnetic field of a planet may not seem important, but on a world like K218b, it could make or break the chances of life living. Without a magnetic field, a planet is defenseless against the rage of space. Solar flares, stellar winds, and cosmic radiation can strip away atmospheres, bombard surfaces with deadly particles, and sterilize everything in sight. Earth's magnetic field acts like a force field, deflecting high-energy particles and keeping our atmosphere intact. Without it, we'd be a scorched, barren world like Mars. So, does K218b have a magnetic field strong enough to keep its strange atmosphere and whatever might be swimming below it safe? The first thing that makes a magnetic field is that which makes it. The magnetic shield around Earth is driven by the moving of iron molten in the Moon's outer core. As the planetary movement and convection make the liquid metal swirl, it makes a geodynamo, which is an electromagnetic engine that runs on its own. Believe how that process would work on a planet 8 times heavier than Earth. It is possible for K218b to have a strong magnetic field if its core is made of rocks or metal, and it is still hot enough to churn. Its size and weight alone make me think that it might have a much bigger dynamo effect than Earth, especially if it spins very quickly. We don't yet know how fast K218b spins. If it's tidally locked, with one side always facing its star, then the rotation might be too slow to drive a magnetic field. That's one reason scientists are cautious. No spin, no churn, no field. K218b is likely a mini Neptune with a thick hydrogen-rich atmosphere. This matters because hydrogen is light and easily lost to space unless protected. A magnetic field would be essential to prevent atmospheric escape, especially from X-ray and ultraviolet radiation emitted by its red dwarf star. And while K218 star is relatively calm compared to other red dwarfs, even mild flaring over billions of years could slowly strip the upper atmosphere unless something is there to deflect it. In fact, we've seen this happen in other systems. Planets with no magnetic field tend to lose their air quickly, especially around active stars. Some scientists speculate that hydrogen-rich atmospheres themselves could generate a magnetic response under the right conditions. If the planet's atmosphere is conductive enough, due to ionized particles or deep pressure-induced metallic layers, it might host a magnetic field not from a metallic core, but from the movement of charged gases. This is similar to how Jupiter generates its own enormous magnetic field, not from an iron core, but from its layer of metallic hydrogen deep inside. K218b may follow a similar pattern, especially if pressure in its lower atmosphere crushes hydrogen into a metallic state. If that's happening, the atmosphere itself might be the dynamo. Beyond just stopping radiation, a magnetic field might be useful in other ways. It might help keep the climate steady, stopping it from falling apart or getting too rough. As well, it could trap charged particles from the star, creating shows that look like the northern lights on Earth and could possibly be seen by future telescopes. But how do we know if K218b has a magnetic field at all? This is one of the hardest problems in the study of exoplanets. From Earth, 120 light-years away, we can't send a spaceship with a magnetometer. There are, however, a few secondary ways to do it. One way is to look for radio signs. Radio waves like the ones we see coming from Jupiter might be made when a star's strong magnetic field interacts with its wind. One more way is to keep track of how fast the planet's atmosphere is leaving. If the hydrogen layer stays put for a long time, it could mean that a magnetic field is there to keep it there. Scientists also look into how the planet's magnetic field affects the magnetic field of its star. If the planet's light curve changes in strange ways, or the star's flares act in strange ways, that could be a sign of a magnetic effect. Future telescopes like LUVOIR or the Square Kilometre Array, SKA, may be able to detect these faint signs of magnetic activity from faraway worlds. It's not impossible, just difficult. But the payoff would be huge. If K218b has a magnetic field, that adds a major point to its habitability scorecard. It would mean its atmosphere could last billions of years. Life wouldn't be constantly fried by radiation. The chemical balance of its air and ocean would be more stable. The timescale of life's evolution. Could it be older than Earth? We often look for planets that are like Earth in terms of size, weather, and temperature when we think about the search for life beyond Earth. But time is something that is often forgotten. It's been around for how long? What's more, how long has life had to change there? K218b orbits a red dwarf star named K218. red dwarfs are the most common stars in the galaxy, and they live for trillions of years, much longer than our Sun, which has a projected lifespan of about 10 billion years. But K218 in particular is estimated to be around 6 to 8 billion years old, possibly older than our Sun. That means K218b has had a longer clock ticking than Earth has. What does that matter? Well, life started to form on Earth pretty quickly, within a few 100 million years of the planet's creation. But living a complicated life took a lot longer. Intelligent life like humans didn't develop until the last few million years, which is a blink in the history of the universe. Multicellular animals didn't appear until about 600 million years ago. Now think about what would happen if a world had 2 or even 3 billion more years to work with. What might life be like if it got that much ahead of time? If K218b has been stable for billions of years, and liquid water has been on or below its surface for most of that time, then there is a much greater chance that life will change into something complex or even smart. There isn't intelligent life there just because this is true, but it means that the time frame would allow it. On Earth, evolution has been tightly coupled with planetary changes. Mass extinctions, oxygenation events, ice ages, they all shaped the course of life. More time gives more chances for life to diversify, adapt, and recover from catastrophic events. And in a water world like K218b, those conditions might be even more favorable. If the ocean is deep and stable, and if it's been shielded from harmful radiation by a thick atmosphere or magnetic field, evolution could proceed more smoothly than it did here. In fact, without major extinction-level events, like the asteroid that killed the dinosaurs, life might progress faster. Another wrinkle: red dwarf stars like K218 are tricky. While they live long, they're often extremely active in their youth. Massive flares and high-energy radiation are common in the first billion years of a red dwarf's life. That could have sterilized K218b early on, unless life started later or survived underwater, where UV light can't penetrate. It's possible that K218b had a delayed start, a billion years of chaos followed by billions of years of calm. In that case, life may have evolved later than on Earth, but still had more total time to diversify. The presence of molecules like methane, carbon dioxide, and dimethyl sulfide in the planet's atmosphere suggests something is happening now, something possibly biological. Whether it's simple microbes or more advanced oceanic life, that timeline matters. We should also consider the implications of life evolving under a hydrogen-rich atmosphere. Some scientists believe that the lower UV levels around red dwarfs could actually make mutations, the fuel of evolution, slower. But others argue that radiation from the star's flares could actually provide occasional bursts of genetic variation. That's the evolutionary sweet spot. Not too much to destroy, not too little to stagnate. If K218b has had a mostly quiet star for the past several billion years, the conditions might have been just right. There's another angle to consider: plate tectonics and climate cycles. On Earth, plate tectonics have played a huge role in nutrient cycling, climate regulation, and biodiversity. We don't know if K218b has tectonics, but its internal heating and gravity might produce similar recycling mechanisms, possibly through underwater vents or mantle convection. This could provide a stable, nutrient-rich environment for life to flourish over deep time. And if evolution has had time to run its course, we could be dealing with life forms that are biologically or chemically very different from Earth life, but no less advanced. In fact, in some scenarios, it's been speculated that long-standing ocean worlds might produce intelligent life forms adapted to water, darkness, pressure, and chemical gradients. Not land-walking bipeds, but perhaps networked soft-bodied organisms with hive minds, sonar-based language, or even photosensitive skins. Now let's be clear, none of this is proven. This is the cutting edge of what people think about aliens. But what really makes K218b interesting is that the timeline backs it up. The clock has been going for a while. It's been going longer than ours. There may be a lot more life on this planet than on Earth, since time is one of the main factors in development. How long would a signal from K218b take to reach Earth? Let's say that K218b has life. Not just microbes, but also clever, technologically advanced beings that can send messages through space. If they sent a message to us, how long would we have to wait to hear it? That's the big question. K218b is located roughly 120 light-years away from Earth, in the direction of the constellation Leo. That means a message sent from there would take 120 years to reach us, traveling at the speed of light, the fastest speed possible in the universe. The number 120 is more than just a fact. It serves as a reminder of the time difference that comes with communicating across galaxies. It would take another 120 years to get back to them if we sent one. It takes 240 years to go both ways for just one deal. In order to understand what's going on, picture if a society on K218b had sent a radio signal to Earth in 1905. It would be sent to us right now, while we look at pictures of their world taken by James Webb. Earth had just started making airplanes in 1905. Albert Einstein had just put out his theory of special relativity, and there was no such thing as TV. That's the kind of gap in history we're talking about. So even if we heard something today, we'd be listening to their past, possibly their ancient past. This has some profound consequences for the search for extraterrestrial intelligence. SETI. If an intelligent species lived on K218b and had a spacefaring or technologically capable civilization in the past, they may have long since gone extinct by the time we hear their signal, or they may have evolved into something else entirely, or they might still be around, waiting for a reply they sent out centuries ago. But what kind of signals could we receive? Most likely, they'd be radio waves, laser pulses, or perhaps some other form of electromagnetic communication. These are the most efficient methods we know of to transmit information across interstellar distances. Radio waves in the 1 to 10 gigahertz range, known as the microwave window, are particularly attractive because they travel easily through space with little interference. Beams spread over 120 light-years. Even a tightly focused signal spreads out. Imagine a flashlight beam expanding across a football field. By the time it hits your eyes, it's a faint glow. A signal from K218b would require extreme power or precision to still be detectable here, unless it was aimed directly at us. This is where the idea of a beacon comes in. If an advanced civilization was intentionally broadcasting across the stars, they might aim a signal toward habitable-looking star systems like our own. Or they might use an all-sky method, blasting signals in every direction, hoping someone's listening. In 1974, the Arecibo Observatory sent a radio message toward a star cluster 25,000 light-years away, a symbolic gesture more than a real attempt at contact. We've also launched records aboard the Voyager spacecraft and beamed out math-based messages hoping to be understood by alien minds. But the truth is, we don't even know if anyone is listening. What if they sent a warning before we saw it? That is yet another annoying thought. Radio waves can go on forever, but our ability to pick them up is limited. We wouldn't have been able to pick up a signal from K218b if it came to Earth in, say, the 1800s. It would not have been seen unless it was still moving through space or repeating itself like a light. Were we not looking in the right place, could we have missed a signal? Of course, our listening stations and telescopes don't always and across all frequencies scan the whole sky. That's getting better thanks to SETI projects like Breakthrough Listen, but our search is still pretty narrow. To have the best chance of finding something strange, we might have to wait until a special camera focuses on the K218 system during one of its transits. This would happen while JWST and other equipment are already watching the planet. It's also possible that an alien civilization wouldn't use radio at all. Some scientists believe advanced species might use neutrino signals, quantum communication, or gravitational wave modulation, techniques we haven't even mastered yet. If they're using tech far beyond ours, we might not even recognize their messages as signals. It'd be like sending a podcast to an ant using Bluetooth. Searching for technosignatures. Are we listening in the right frequencies? It's one thing to find hints of life on an alien world, molecules like water vapor, methane, and dimethyl sulfide swirling in its skies. But it's something else entirely to ask. Is anyone out there trying to reach us? That's where the search for techmarks starts. Technosignatures are the signs or evidence that technologically advanced societies leave behind. Biosignatures are signs of life like microbes or plants. Technosignatures, on the other hand, are signs of much more advanced life, like civilizations making tools, sending messages, or even collecting energy from their stars. K218b is now in the spotlight. With its 99.7% probability of biological activity and a hydrogen-rich oceanic environment, it's the first exoplanet in the habitable zone to show atmospheric signs that resemble Earth's. Naturally, the next step for many scientists is to ask, could there be intelligent life there? And if so, are they broadcasting? The places we look might not be right, or the best ways. These days, most studies for technosignatures are focused on radio waves, especially those in the 110 GHz range. This is the electromagnetic spectrum's quiet zone, where cosmic background noise is low and air interference is low. People have been sending TV messages, military radar, and satellite signals on this band for a long time. Programs like the Breakthrough Listen Initiative are scanning billions of frequencies from thousands of stars in this range, including stars like K218. But K218b wasn't originally a technosignature target, until JWST changed the game. Now it's a prime candidate. Scientists are beginning to monitor the system more closely, tuning in during transits and flare events to catch any unnatural blips. So far, nothing, just static. But silence doesn't mean absence. It could mean we're just not aligned. If an intelligent civilization on K218b is using a narrow targeted beam, say a laser communication system like those we're developing ourselves, it might not be pointing at us. A 1-degree misalignment would mean Earth gets nothing. And if it's a directed signal meant for another star system, we'd never know it was happening. Then there's the issue of frequency choice. What if K218b's inhabitants use something completely different, like terahertz pulses, X-ray modulation, or even quantum-entangled particles? These methods are theoretically possible and might allow for near instantaneous communication over vast distances. But we haven't developed the tools to detect them on a cosmic scale. Is there one more wildcard? Small files and security. We might not be able to figure out how an alien signal is encoded. It could be wrapped in complex math, squished into fractal patterns, or hidden in what seems like random noise. Because SETI systems depend on finding clear mathematical signatures or repeated patterns, that kind of information might not be picked up at all and get through our filters. But that doesn't mean we have no other choices. Some of the most promising studies for technosignature don't involve listening at all. Instead, they look for signs of alien technology. Scientists are now looking at exoplanets to see if their atmospheres have any strange chemical changes, like pollutants from factories that wouldn't happen in nature. Also, they are looking for stars that dim in strange ways, which could be caused by big structures such as Dyson swarms or orbital screens. One sign could be the use of manufactured energy if they see more heat than expected leaking into space. This is called an infrared overflow. The way a star's light flickers might show strange geometric patterns that could lead to satellites in space that were built by a smart species. If K218b had a technologically advanced society using energy on a planetary scale, we might eventually detect signs of waste heat, orbital patterns, or citywide light. So far, JWST hasn't seen anything that jumps out, but it also wasn't designed to look for cities or Dyson spheres. Its instruments are geared toward chemistry, not civilization. The truth is, we're in the earliest stages of technosignature detection. We don't know what we're looking for, and we've only been truly searching for a few decades. By comparison, the Earth has only been broadcasting detectable signals for about 100 years. If every alien civilization follows a similar arc of rising and collapsing technology, we may just be in the wrong time frame. Civilizations might flash into radio visibility, then vanish in centuries, blink, and we miss them. That's why many scientists argue for passive listening and long-term commitment. Rather than blast the sky with messages, which could be risky if hostile civilizations exist, we focus on listening, quietly, patiently, across frequencies we haven't even discovered yet. Can JWST directly image the planet one day? At this point, everything we know about K218b comes from secondary data, mostly light curves and spectra. Jupiter has been photographed by the James Webb Space Camera, JWST, but not in the same way that you'd take a picture of Jupiter with a home camera. We see things by putting together how the planet changes the light from its star. That includes drops in light during transits and very small spectral marks left by molecules in its atmosphere. However, what if we could see K218b directly? Not as a spot or a fuzz, but as a world with clouds, oceans, and maybe even man-made lights. That's the dream of direct imaging, and it's not as far-fetched as it sounds. JWST is incredibly powerful, but it's optimized for infrared spectroscopy and transit analysis, not for taking visual light photographs of planets next to their overwhelmingly bright stars. A red dwarf like K218 is dimmer than our Sun, which helps, but the contrast between the star and its planet is still on the order of 1,000,000 to 1. To spot a faint glowing orb just pixels away from a dazzling light source is like trying to photograph a candle beside a spotlight through a foggy window from across the street. JWST does have a few tricks up its sleeve, like coronagraphs, devices that block starlight so fainter objects nearby become visible. But these coronagraphs weren't designed for planets as close to their stars as K218b is. They work better for big gas giants on wide orbits, far from the glare of their parent suns. So, for K218b, JWST probably won't get us a photo just yet. Future missions are being built with direct imaging as the main goal. Take LUVOIR, Large UV Optical Infrared Surveyor, a proposed NASA space telescope the size of a tennis court. Its mirror would be 4 times bigger than JWST's, and it would use advanced coronagraphs and starshades, massive flower-shaped shields flying thousands of kilometers away from the telescope to block out starlight with precision never seen before. With LUVOIR or its cousin HABEX, Habitable Exoplanet Observatory, we could get high-contrast images of Earth-sized planets in the habitable zones of nearby stars. That includes red dwarf systems like K218. In theory, these telescopes could isolate the light of K218b, break it into colors, and reconstruct images showing everything from planet-wide weather patterns to surface reflectivity. And yes, maybe even city lights on the night side. There's also a concept known as nulling interferometry. This involves multiple telescopes working together to cancel out starlight by using destructive interference, essentially erasing the star from the image so the planet stands alone. The European Space Agency once proposed such a system in the form of Darwin, and while it was shelved, newer, smaller-scale versions are back on the table. Back to JWST. Could it still do something close to direct imaging for K218b? Well, not a full picture, but what it can do is make ultra-precise measurements of how the planet's brightness changes over time. These phase curves tell us how reflective the atmosphere is, whether clouds form and move, and even if the night side has any glowing infrared heat, perhaps from volcanism or deep oceans. That's not an image in the traditional sense, but it's the next best thing. Another clever method is called secondary eclipse measurement. This happens when K218b moves behind its star from our point of view. During that moment, the total light we see drops slightly, because the planet's own glow is briefly blocked. That missing bit of light helps scientists estimate the planet's temperature, both at the surface and in the atmosphere. It's not an actual photo, but it gives us valuable data to build detailed models of what K218b might be like. As for directly imaging the planet, that's much harder. To pull it off, We'll need a larger telescope with more power, a better coronagraph, or even an external star shade to block out the star's glare, and ultra-sensitive detectors that can pick out the planet's faint light from all the background noise. Levois and Habex both check those boxes, but there's a long wait. Neither is expected to launch before the late 2030s or early 2040s. Even then, K218b isn't a guaranteed target unless it's added to the observation priority list. Political, budgetary, and technical decisions over the next decade will decide what happens. How the 99.7% estimate has divided the scientific community. It was like a cosmic mic drop when the news came out that K218b might have a 99.7% chance of life. The news stories blew up. The internet was full of talk about aliens, but in academic groups and science papers things were much less clear-cut. Some would even say they were split down the middle. To the public, a number like 99.7% seems definitive. It sounds like a guarantee. But to scientists, especially those in astrobiology, that number is just one piece of a complex puzzle. And how you interpret that puzzle depends on your assumptions, your field of expertise, and your tolerance for risk. Let's start with what that 99.7% actually means. It didn't come from some magical alien detector. It came from Bayesian atmospheric modeling, a statistical method where you feed in known data, in this case light spectra from the James Webb Space Telescope, and run simulations using different atmospheric compositions. Each model tries to recreate the observations with different combinations of gases, like water vapor, methane, carbon dioxide, and dimethyl sulfide, DMS. The model that included biological sources for these gases matched the observed data better than any non-biological model. In statistics speak, that gave a posterior probability of 99.7% in favor of a biological explanation. But here's the catch. Bayesian models are only as good as the priors you feed into them. And that's exactly where the scientific community begins to fracture. Some astrophysicists argue that the priors used in this analysis may have assumed too much about the possibility of life. In other words, they worry that the model was biased toward life from the start. If the assumed prevalence of life-friendly conditions is high, then naturally the output will lean toward life. Skeptics say we need far more neutral or even hostile priors to see how robust the result really is. Others say that dimethyl sulfide, DMS, one of the chemicals that was found, is only made by living things on Earth, especially phytoplankton. That alone made the news. But the question is, could DMS form without living things on a world like K218b that has a lot of hydrogen in its ocean? Some chemists and planetary scientists say yes, but only in very unlikely situations that we haven't fully modeled yet. In other words, the DMS finding might not be the sure thing biosignature that it has been made out to be. Different scientists, those who study biosignature false hits, are also worried about something else. They stress the chance of noise from the instruments or mistakes in the tuning. There are so many light years between us and the planets we're trying to find that it's like trying to smell a perfume bottle from across a stadium. With just one mistake in the instrument, or one cosmic ray hit that was missed, the signal could be off. Researchers like these say to be careful and do more tests before coming to any big conclusions. Yet, not everyone is skeptical. A large number of astrobiologists and planetary modelers are electrified by the 99.7% result. They point out that for the first time we're seeing not just one gas, but a trio of potential biosignatures, methane, carbon dioxide and DMS, coexisting in the habitable zone of an alien world. That combination, they argue, is statistically improbable through non-biological means. To them, it's a case of the biosignature cocktail being too perfect to ignore. Then there's the community of SETI, Search for Extraterrestrial Intelligence researchers, who approach things from yet another angle. They argue that this 99.7% probability, even if not conclusive, radically shifts the search field. Instead of casting a wide net across the galaxy, we now have a specific target, K218b. Some are already lobbying to aim radio telescopes in that direction, just in case a signal awaits. The divide also plays out in how different journals treat the data. Some have fast-tracked papers on K218b's potential for life. Others have requested extended peer review or demanded that disclaimers be added to temper expectations. Even at scientific conferences, the debates have gotten heated. One astrobiologist reportedly compared the hype around K218b to the infamous arsenic life debacle of 2010, where early claims of alien biochemistry eventually collapsed under scrutiny. Simulating K218b in labs, creating its atmosphere on Earth. Astronomers aren't just thinking when they say K218b might have life. They're putting it through tough tests to find out. But how do you check out the sky of a planet 120 light-years away? It's made in a lab. On Earth, researchers are now recreating the alien atmosphere of K218b, complete with hydrogen gas, exotic pressures, and eerie cloud conditions, to see what happens when you introduce biological and non-biological processes. This isn't science fiction. It's real cutting-edge experimental astrobiology. K218b's atmosphere is believed to be hydrogen-rich, with traces of water vapor, methane, carbon dioxide, and dimethyl sulfide, DMS. To study how such an environment behaves and whether life could produce these chemicals, scientists use simulation chambers. These are sealed containers, often made from quartz or stainless steel, that allow fine control of temperature, pressure, and gas composition. Think of them as miniature exoplanets in a box. One of the leading facilities for this kind of research is NASA's Astrobiology Institute, where planetary atmosphere chambers are used to mimic conditions from Mars to Titan to now, Hycean worlds like K218b. Another hotspot is the University of Cambridge, where researchers have been building Hycean models to test how biosignatures evolve and interact in hydrogen atmospheres. These labs are pushing one critical question. Can life realistically produce the chemicals seen by JWST under these alien conditions? To find out, scientists load the chamber with the suspected atmospheric mix of K218b, about 95% hydrogen, with small amounts of methane and water vapor. Then they introduce two key variables, ultraviolet light, to simulate the red dwarf's radiation, and biological agents, like plankton, bacteria, or even enzymes. The chamber is sealed, the experiment begins, and the gas composition is monitored over time. We can already see some very interesting trends. For instance, some Earth germs can still live in places with a lot of hydrogen, especially methanogens and sulfur-based bacteria. These extremophiles, living things that can survive in harsh conditions, don't need air. As a waste product, they make gases like methane and DMS. While they are in the lab, some bacteria do even better in hydrogen than in nitrogen or carbon dioxide. That's a big deal. It means that DMS, the chemical found by JWST that is linked to life, might be able to be made naturally in a Hycean world. What about false results, though? That is the other part of the test. To rule out non-biological origins, scientists rerun the same experiments without any life present. They simulate volcanic gas production, photochemical reactions, and hydrothermal vent emissions. In many of these sterile simulations, methane and water vapor still appear. But DMS? It doesn't show up, or if it does, the levels are negligible compared to the bio-rich chambers. That contrast becomes a fingerprint. Life leaves a stronger chemical signature, one we may be seeing on K218b. Another experiment explores what happens to these gases over time. In a hydrogen atmosphere, UV light breaks down DMS quickly, within hours or days. This means that for DMS to stay detectable, something must be replenishing it constantly. That's a subtle, powerful argument for ongoing biological activity, not just a one-time geological burp. Beyond the gas composition, these labs also study cloud formation and haze. Using high-pressure reactors, they can condense water vapor and other volatiles to see what types of clouds might form in a Hycean sky. Preliminary findings suggest thick, high-altitude clouds, possibly bluish or grey, could blanket a planet like K218b. These clouds would obscure the surface but still let spectral signals escape, matching JWST's data. Now, none of this confirms life on K218b, but it does do something crucial. It shows how Earth-based experiments can test alien hypotheses, and that's a new era for astrobiology. We're not just waiting for telescopes to find life. We're rehearsing its discovery, running simulation after simulation to separate signal from noise, hope from hype. And the models are getting even better. Some labs are now using AI models to guess how biospheres that we don't know much about might act. Some people are looking into deep ocean biospheres by adding wave stress and fake magnetic fields. It's an exact copy of alien worlds, but there aren't any aliens there yet. Why K218b is a turning point in astrobiology. Astrobiology has come a long, careful way, from thinking about Martians to studying dust grains in the space between stars. But there has never been a time quite like this. K218b used to be just another red dwarf world in a long list of them, but now it's a key part of how we think about life beyond Earth. Not because it looks like Earth, but because it's strange in just the right ways. The detection of key molecules, methane, carbon dioxide, and possibly dimethyl sulfide, DMS, in its atmosphere signals something bigger than just an intriguing planet. It marks the first time in human history that a telescope, specifically the James Webb Space Telescope, may have observed biosignature candidates on a planet in the habitable zone of another star. This is not the same as finding life, but it's a massive upgrade from past exoplanet discoveries. For decades, astrobiology was based on speculation, indirect measurements, and analogues from Earth's biosphere. We talked about Goldilocks zones, potential oceans under ice, and rocky planets around sun-like stars. But everything was a guess or an extrapolation. K218b changes that. What makes this planet such a turning point is how unexpected its features are. It's not a classic Earth twin. It's not a dry, rocky planet with blue oceans and continents. It's a Hycean world, a class of planet that didn't even formally exist in planetary science discussions until a few years ago. A Hycean planet is a hybrid, hydrogen-rich atmosphere, likely covered in a deep global ocean, and possibly several times the mass of Earth. Not exactly Earth 2.0, but potentially even more habitable in some respects. The Earth-centered model of life has been a bias in science for a long time. The fact that such a world might have signs of biological activity pushes us to face this bias. People have been looking for biosignatures for decades in atmospheres like Earth's, with things like oxygen, nitrogen, ozone, and so on. But JWST's results make us look at things with a bigger picture. Life might be able to survive in atmospheres high in hydrogen, but it might have metabolisms and chemical paths that are very different from what we've thought of. Before this, it was hard to get more information about even the most well-known possibilities for habitable zones, like TRAPPIST-1e or Kepler-442b. It was either too thin, too dark, or just too far away to reach them. But K218b has a better spectral signal because it is bigger and has a thicker shell of gas. That means scientists can get a better look at its atmosphere, especially in the infrared range, which is what JWST does best, and what JWST saw is game-changing. The planet's spectrum shows strong signals of water vapor, suggesting clouds, maybe even rain. Methane and carbon dioxide are present in ratios that aren't easily explained by non-biological processes. But the wildcard is DMS, a gas that on Earth is exclusively produced by life, particularly marine plankton. If that signal holds up under scrutiny, it would be the first potential detection of a biosignature on an exoplanet. This has transformed how scientists approach the search for life. K218b is now a testbed for every new idea in astrobiology: chemical disequilibrium, biosignature survivability, the role of stellar activity, atmospheric escape, and more. Theoretical models are being recalibrated based on its data. Lab experiments are being redesigned around its atmospheric conditions. And most importantly, new exoplanet survey strategies are emerging, with more attention now being given to mini-Neptunes and sub-Neptunes that may have Hycean profiles. Even the definition of habitable is being rewritten. Previously, if a planet didn't have Earth-like pressure, temperature and oxygen, it was written off. But K2-18b, with its exotic chemistry and high pressure, could be far more hospitable to microbial life than Earth-like exoplanets that are dry and barren. There's also a psychological shift happening. Until now, discussions of life beyond Earth were seen as speculative, distant, or even fringe by some corners of the scientific community. K2-18b changes the tone. It provides something solid, a dataset, a signature, a reason to ask the question, not just philosophically, but scientifically, methodically. NASA's press conferences, ESA briefings, and even university classrooms are treating K2-18b as more than just another planet. It's becoming a case study, one that blends astronomy, chemistry, biology, and planetary science into a real-world investigation of life's cosmic potential. What if the biosignature vanishes in future data? The risk of overhyping. The moment JWST data hinted at the presence of dimethyl sulfide, DMS, in K2-18b's atmosphere, the world lit up with headlines. Life found on another planet? 99.7% chance of biology. The buzz was loud. But science isn't built on buzz. It's built on repetition, skepticism, and the slow burn of confirmation. Which raises a sobering possibility. What if future observations show nothing? What if DMS vanishes? It's not crazy to worry about this. It's normal for exoplanet scientists to find false findings. There are a lot of small factors that can change spectral patterns, especially those that are close to the detection level. There is noise in the sensor, errors in calibration, out of whack wavelengths, space rays. It is possible for results to be misunderstood even if assumptions are built into the data models. That's why scientists have been cautious, even as the public gets swept up in the hype. In JWST's case, the DMS signal was described as tentative, a low-confidence bump in the spectrum, not a smoking gun, a whisper. There's precedent here. Back in 2015, astronomers thought they had detected oxygen on the exoplanet GJ 1132b, but further studies suggested it was likely an artifact, a misread caused by the planet's haze layers. More recently, the detection of phosphine on Venus sparked global excitement as a potential biosignature. Months later, it was revealed that the signal may have been exaggerated, or perhaps not even real. It wouldn't mean the science was bad if K2-18b's DMS signal went away in later samples. That would mean that science is correct. Confirmation bias is not good for science. It lives in trouble. Better data, sharper tools, and tougher models must be able to test every idea. And the next observations that JWST will make, which are set to happen between 2026 and 2027, will do just that. They will look at the DMS finding very closely. One risk here is not just scientific disappointment, it's public backlash. The media has already jumped to calling K2-18b a life-harboring planet. If those claims are walked back, people might feel misled. So it was all fake? They'll ask. The danger isn't that we didn't find life. The danger is losing public trust in how science communicates. That's why astrobiologists are trying to thread a tightrope. Be excited, yes, but don't promise anything. Use language like candidate biosignature, not proof. Emphasize that these are hypotheses, not conclusions. And most importantly, keep reminding the public that this is the beginning, not the end. Even if the DMS signal fades away, the water vapor detection remains rock solid. The presence of methane and carbon dioxide is still significant. These alone make K2-18b one of the most promising exoplanets we've ever found. The possible biosignature isn't the only story, it's just the loudest right now. And if DMS isn't there, that's not a loss, that's a refinement. Science often moves 2 steps forward, 1 step back. Remember how Pluto was once called the 9th planet? Or how cold fusion was once a media darling? These aren't failures. They're part of the system. The self-correcting loop that makes science better than rumor, better than dogma. The experts who put their careers on the line with this early analysis are under a lot of pressure. Return on investment is a big question for people who are supporting future space trips. And regular people who read the news and thought of alien seas, skies and microbes would feel like the world had just shut the door again. But just maybe, that's not such a bad thing, because being disappointed makes you stronger. If K218b turns out to be a false start, it will help us find the next possibility more quickly. We'll learn what noise looks like, how fake hope smells, and how to make tools that can cut through the fog better. Are there other K218bs out there? How common are Hycean worlds? K218b might look like a cosmic accident, a rare gem hidden 120 light-years away with an atmosphere that is good for ocean life and a hint of life. What if it's not that rare? What if the galaxy is full of thousands of K218bs? What if they are all ocean worlds hidden under hydrogen skies, each one quietly boiling with potential? Hycean planets, short for hydrogen-rich ocean worlds, are a relatively new category. They're not gas giants, not rocky like Earth, and not ice balls like Neptune's moons. Instead, they occupy a sweet spot. Super-Earth to mini-Neptune in size, with atmospheres thick in hydrogen and surfaces potentially covered in deep oceans. It's an idea first proposed seriously in the early 2020s, and now it's exploding across exoplanet science. Why? They're everywhere. Something strange showed up when scientists looked at data from Kepler and TESS. Planets that aren't Earth-sized are the most common type in the sky, something a little bigger, about twice or 3 times the size of Earth. It's easy to miss these worlds because they are not in our solar system. But they control star systems around red dwarfs and even stars like the Sun. That means planets like K218b, massive enough to hold a hydrogen envelope, but not so large they become gas giants, are not rare. Statistically, they might outnumber Earth clones 5 to 1 in our galaxy. Now combine that with the fact that Hycean planets could have much larger habitable zones than Earth. Their thick atmospheres trap heat efficiently. That means even if they're farther from their star, they could still host liquid water. And in some cases, their internal heating could support subsurface oceans even without stellar warmth at all. Scientists searched for life for many years by focusing mostly on planets like Earth. A rocky surface, a thin atmosphere of nitrogen and oxygen and liquid water. Is there anything else? It's too strange. Too strange. Ocean worlds fight that bias. What if Earth isn't the best place for life? What if alien life likes a different mix of chemicals, like warmer air, higher pressure, darker skies, and slower days? In an ocean world, you might not be able to walk on the beach. You could swim through a hazy ocean with a thick pink sky and a dim red star shining through it. It wouldn't be like life here. Breathe like we do. It might not even move like people. Still, it might be possible. In fact, many Hycean worlds might be better for life than Earth. Why? Because they offer more environmental stability. Earth has continents, ice ages, asteroid impacts, shifting tectonics. That's exciting, but it's also dangerous. Hycean planets, by contrast, may have fewer land-based catastrophes. Their deep oceans and dense atmospheres could insulate life from harsh space weather. If biology evolves there, it might enjoy a longer, more stable runway to become complex. Some Hycean candidates already turning heads include GJ1214b, a steamy super-Earth covered in clouds, TOI 270d, sitting comfortably in its star's habitable zone, and HD 106906b, an extreme outlier that might be forming a moon-rich system of its own. So how do we find more of them? JWST is just the beginning. It can study a handful of nearby Hycean planets, but future missions like the European Space Agency's Ariel, NASA's Habex, and Le Voir are designed to scan hundreds. These telescopes will read atmospheres, detect biosignatures, and build a statistical profile of life-friendly planets. If just one of these Hycean planets, out of hundreds we'll observe, shows solid biosignatures like DMS methane or oxygen, it changes the equation completely. Instead of asking, is there life out there? We'll be asking, how many billions of life-bearing worlds did we overlook? It's the Copernican principle again. Earth isn't special. And if Earth isn't special, K218b isn't either. It might just be the first raindrop in a Hessian downpour. If K218b really does have life, even if it's only tiny, we might be seeing the first real sign that we are not alone. And if this is only the start, just think of what else is out there, hidden by the stars. Thanks for watching. If even a small part of this blew your mind, please like, follow, and leave a comment below to share your thoughts with us at Beyond Horizons.